Great. Okay. Okay. Great. Thank you very much for.
Apologize for the delay.
No worries. That's exciting. Okay. So this tutorial was created, as I mentioned, as part of a course. But the other part also is a survey, which I will give the URL later. It took 2 years to do this survey, 256 papers. And what really is different from other survey on multimodal is that it is not centered around the algorithms or around the application, but around the core challenges from a mathematical perspective when you look at multimodal. That's really the way we look at it, and that's what the tutorial is centered around. We were supposed to be 2 of us to give this tutorial, Tadas Baltrozatis. He just had a baby. So it's a beautiful and wonderful reason for not being here. That also means I will have 3 hours of show time. Which I don't mind. I love talking, so that's not an issue for me. But as I mentioned, if you're not asking questions, it's going to be a really one-way conversation. So this is slightly older pictures of my group. I moved to Carnegie Mellon about 3 years ago. Before that, I was at University of Southern California. Los Angeles was too sunny for me, so I moved to Pittsburgh. Pittsburgh is beautiful, and I'm originally from Quebec, Canada, so it's somewhere in the middle. The group is my group, and this is the only slide I have on my group because this tutorial is not about my research, but really about how multimodal research in general. But my group works on algorithms to analyze, model, and generate human subtle communicative behavior. So I'm really interested what I would call the 3V of communication: verbal, visual, and vocal. As I mentioned, this was supposed to be 2 people on this. Tadas will not be able to join, and I already mentioned that this was based on a course. If you're interested to gain access to the slides of this larger course, you have to contact me directly. I can give you access to the Piazza, and I will also put all of these slides available after the tutorial. I have to see where we're going to put them, but they will be available for people. So the tutorial schedule, maybe I don't like being on the podium, so if anything, it's going to be a challenge for the recording, but this is a 6-part tutorial. The first part will be about introduction, what is multimodal, and why multimodal, and really the core technical challenges of multimodal. That's what we will be discussing. We will go through some basic concept. This is a tutorial, this is not a research talk. So we'll go through some basic concepts so we're all on the same page, looking at linear model, neural network, and optimization. And then unimodal representations. I will not spend time on language as a representation. This is something you guys know already or should know. I'm happy to. I have plenty of slides on language. I will not focus on that. Instead, I will focus on representation that are a lot more popular in visual and vocal modalities. Then we get into the core, multimodal representations. And as you will see, and I will give you more details, the idea of multimodal has 5 more challenges, 5 main challenges, but each of them has subclasses. And so, for example, in multimodal representation, there's work on joint representation, but also on coordinated representation. And we'll look at this at the same time. We'll have at least a coffee break, and we'll see when it happens. It depends on how many questions you ask. Then we'll do some very basic concept also on recurrent neural network, again, so that everybody is on the same page, before starting to talk about translation and alignment. Alignment is very interesting because there is the idea of alignment as an explicit task or alignment as a latent or implicit task. And finally, we'll talk about multimodal fusion, both model-based, but also some of the model-free approach and then some of the model-based approaches. So this is what we're going for. We're going for 3 hours of this. What is multimodal? What is multimodal? Why did you come here? Did you get the wrong room? Yeah, so multimodal. What is, from your perspective, what is multimodal? In fact, yes.
Multimodal is, it means that it uses different modalities, right?
Mm-hmm.
So it can use like, I don't know, speech, vision, or some other modalities.
Exactly, and so there's many definitions of multimodal. The one you gave is probably one of my favorite, looking at multiple modality or communicative modalities. That's the one we will focus on. If you had to go like the most generic definition of multimodal, I would say it's the science of heterogeneous data. Heterogeneous data meaning data that is different modality but also could be different nature on it, and we talked about multiple cues earlier. So from a really generic manner is science of heterogeneous data, all the way to more specific about looking at modalities of communication. In fact, if you look and you look on Google Scholar, what is the earliest paper you see on multimodal? The earlier version of it, multimodal is a multimodal distribution. But this is not what the tutorial is about. So if you were here for multiple mode in a distribution, we're not looking at that. There's interesting work on this. But this was the original distinct peaks or mode of a distribution. What we are looking at, as was just mentioned, is communicative modalities. And yes, there are quite a bit of modalities. We'll look at a subset of that in this, as I mentioned, verbal, visual, and vocal. What is the difference between multimodal and multimedia? And more conceptually, what's the difference between a modality and a medium? We need to warm up a little bit, huh? Modality is the way in which something happens or is experienced. Okay? And this is in contrast with a medium. It's a mean to store or communicate information. So in the narrow way, multimedium will be multiple way of communicating, the medium of communication, while the modality is the content in itself. Now, this is the narrow way of seeing it. These days, people are using the term multimedia and multimodal in very similar way. And you see the two communities getting much closer to each other. Some of the earlier work on multimedia was video analysis, but now these days you see a lot more coming together. So modality, sensory modality is a subset of the modalities, that's the one we'll look at. When we look at modalities, there's many different ones. As I mentioned, natural language, visual, auditory, haptic, the touch, smell, taste, and self-motion. This is really interesting. In the ICMI conference, International Conference on Multimodal Interaction, there was a workshop on taste, like food, and from a multimodal perspective. It was a wonderful workshop, very different from what I was used of multimodal. Really interesting. So there's interesting work going on this. There's also physiological sensor, and there's other modalities there. If anybody in medical imaging, there's a lot of work on multimodal, looking at fMRI and looking at different images, fMRI and EEG together. So, but today we'll focus on these three modalities: natural language, visual, and auditory. In fact, from my personal research, I usually call it, as I mentioned, the 3V of communication. The verbal is mostly the spoken words, the choice of words, the grammar, but also the pragmatics. Pragmatics is a wonderful word. What does pragmatics means for you? Okay, here's great, thank you.
So, for me, pragmatics, it means what the person actually meant, right?
The intent really behind the words. And this is where I did put the semantics. So the semantic will be often more the literal meaning of the words, while the pragmatist will be the use of the words and the intent behind. And in a sense, we're kind of mind readers, but what we mean is, what does that person really mean? And there's a lot of interesting theory behind the pragmatics, but when we are analyzing nonverbal behaviors and verbal behaviors together, we often look more at the pragmatics and the intent behind the words. The vocal, I often call it, for the American, maybe it will be a reference, but the 50 Shades of Yeah. The same word, yeah, can have really different meaning. Yeah, 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 yeah. And now you see the facial expression, so you see it in a multimodal way. But there's a lot into how we express. And from a speech perspective, you will have the voice quality. Voice quality will be looking at the vocal folds and seeing the tenseness or the softness, how much pressure you put on your vocal fold. And then as the production of the sounds happen, then you have the prosody, often more in the mouth and the nose, looking at the pitch or the intensity. And then you have the vocal expression. Vocal expression is something that is not based on the words, but it's something extra. So a laughter, a pause filler as an example. Oh, my background, by the way, is computer vision. I got you guys. I'm in an NLP conference. In fact, I'm at one of the largest NLP department at CMU, LTI, Language Technology Institute, but they hired me anyway. They hired me, don't tell them, but I'm a computer vision originally. So I put half of communication as visual. That's my strong bias. But I believe there's a lot into the gesture you're making, beat gesture. There's also a lot in the body language. So when you're talking, at some point there is something like proxemics. And maybe I become a little bit too close at some point of the proxemic. That's not the correct proxemic. But proxemic is also part of body language. There's a lot into this. And as you expect, is this cultural specific. There's a lot of interesting story in that. The eye contact, when I study human communication, eye contact is the first one I look at. Eye contact tells you a lot about the communicative channel, but also cognitive load and sometimes emotion, but primarily cognitive and communicative. And facial expression. There's a long, full study or lecture on facial expressions. Why do people call some emotions as basic emotions? Some emotions are called by Paul Ekman as basic emotions. Why are they basic emotion or basic facial expression? Have you ever, anybody heard that term? Basic emotion, basic facial expression? So the idea here is that some people say, oh, they're fundamental to us. But the real thing and the more empirical view of it is that these facial expressions, sadness, happiness, surprise, fear, disgust, and I'm missing one. Anger, great. These 6 basic emotions are in fact emotions that are expressed the same way across cultures. And the way Paul Ekman did that is more through an anthropological study where he went to Italy, he went to also I think in Africa, and saw that these emotions are expressed the same way through different culture. But these are not the only emotion. If you do emotion recognition, please do not just do these 6 basic emotions. People are showing a lot through their confusion, frustration, engagement. So there's a lot more to visual and facial expression than these basic emotions. But this is a short summary of what I personally perceive as interesting communicative behaviors. And so from the field of multimodal, this is a multidisciplinary field in itself. In fact, usually I talk about psychology as being fundamental from when I teach these courses. Medical imaging does a lot of multimodal. Speech, vision, language, multimedia, robotics, and machine learning. This is why it becomes such a challenge for any multimodal researcher. And that's how I end up probably in an NLP department, because multimodal does not have a home, it has many homes in itself. So this is a first summary of multimodal, but I want to give you a historical view of the multimodal world, and I think multimodal has 4 eras into it. The first era was the era of behavioral, the second computational, interactional, and deep learning. The behavioral era is the most interesting. This is in the 70s. This is when, in fact, behavioral was really multimodal, looking at psychotherapy. And if you think that having good acronyms is a new thing, you should read this one. He had a wonderful acronym, and now these days we're building these proposals using so many acronyms. But one person that you probably know is Geoff Hinton. And his bachelor was in psychology, just to give you a view of where he came from originally. But one person that I have a great respect for is David McNeill, who retired a few years ago, psycholinguist. If you have a chance to read his work on language and gestures, they were fundamental original work. One of the example questions is, what comes first? One of the questions he always had, and I don't know if he got the answer yet, and I hope one day we can get that answer, is how is language and gesture generated? Is it that we're producing language and gesture is just a secondary produce of that? Or is it you have an intent and language and gesture are produced from this? And this is a really fundamental question that goes almost to neuroscience, but one of the interesting discovery was language often preclude or comes before the gesture. So if you're describing something, you often describe it, and then you do the gesture that goes with it. Really interesting work there. But really, at around the same time, there was a lot of work on speech recognition, and then there was the McGurk effect. Who knows about the McGurk effect? Okay, oh wow, so really few. So this is a fun effect, thank you. And so you have to look at the screen. You have to stop looking at the second screen next to you and look at the big screen. And now we're going to play 2 videos. And you have to hear, and it's a multimodal experience, but tell me what you hear into this. So the first video, look at it and listen.
Ba, 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 ba.
Okay.
Ba, ba, ba.
Whoa. He gave. So you heard the first one, and now I'm going to play the second video.
Ba, 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 ba.
Okay, what did you hear the first time? Ba, ba, ba. The second time? Fa, fa, fa. Okay, I'm gonna play. Whoops.
Ba,
Okay.
ba.
I'm gonna play this video again, the fa, 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 but close your eyes, okay? I'm playing it. Whoop.
Ba, 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 ba.
Open your eyes.
Ba, 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 ba.
Okay, what you should have experienced, most of you, and we can do it again, is if you close your eyes, you start hearing ba, ba, ba. And then you open your eyes and you hear fa, fa, fa. What's interesting there is that it is exactly the same audio tracks between the first video and the second video. The only difference is the visual modality. The visual modality in the second one is a different mouth shape. And because of that, your brain wires it really quickly. And it's interesting because I can repeat this video over and over and like say, no, you have to hear fa. And no, you will hear ba, ba, ba. It's just the brain is really, really wired for that. So you can imagine in the 70s, you find out about this McGurk effect. You've been working on speech recognition for a while, and it's been plateaued for a while, and you're like, that's what we were missing, is audio-visual speech recognition. And so this was some of the initial work in a computational era was motivated by the McGurk effect. And there's been a lot of interesting work on audiovisual speech recognition. In fact, the audiovisual speech recognition was also one of the first paper on deep learning applied to multimodal data, was this ICMI 2011 paper. One thing that we learned from this work on audiovisual is that modalities have more than one way of interacting with each other. Sometimes one modality will bring complementary information to the second one. What it means is that it brings something new, and that will, if merging them together, will bring in fact better performance for recognition. But sometimes it's redundant information, supplementary. And 98% of the time for audiovisual speech recognition, it is supplementary, redundant. And the reason is that we have often noisy environment, and so audiovisual allow for robustness. And that's the thing they learned the hard way doing audiovisual speech recognition, is yes, they were motivated by the McGurk effect, that's the 2%, but for 98%, it is a lot more about redundancy and robustness. That's a really good first notion to learn from this previous work. There was a lot of work on multimodal HCI, move this there. There was, if you know Trevor Darrell, who was also my PhD advisor, his first work, famous, most cited work, is not about cafe, but it's about an interface, about moving object in a multimodal world. In fact, Jeff Hinton also had some work on this topic. This is also in the 80s is when suddenly we have all these digital videos, and the field of multimedia really bloomed at that point with the idea of understanding all the video on the internet. As you see, we're still in the middle of that goal, but that was an early work at that point, and there were a lot of multimedia content analysis problems that came from this. At this point in the 80s, a lot of things were graphical models. And you're like, what do you mean graphical models? Everything is deep learning. That's what I've been learning. But no, there was something before deep learning, or in fact, it's somewhere in the middle, depending how you see neural networks. But graphical models, and a lot of extension on graphical model. Factorial, hidden Markov, and couple HMM, all extension of this. As you know, neural networks were really popular in the 70s as well, and convolutional neural networks was also, you could say, invented, although the name was not exactly the same, in the 80s. Now the third era was the interaction. We went from basic HCI and audiovisual to more interaction. Learning how people interact. The AMI project from Europe was one of these landmark, understanding people in a meeting environment. And if you know Sami Benjo, the brother of Joshua, was working on this AMI project back in the 2000s. Now he's at Google. Kalo. Anybody knows about Kalo project? Yes? Oh, thank you. Great. All of you may know then as a side project that came from Kalo. Siri. Siri was a spin-off company. It was not called Siri at that point, but a spin-off from SRI, and that came from Kalo. It was the return of AI, the goal of creating an agent that learn about your behaviors and also can help you from a meeting perspective, or also just an assistant. And the social signal processing happened also around that same time. And I have to thank a lot of great national initiative from NIST. If you have never heard of the term TrekVid, there's a lot of work in multimedia, looking at multimedia content analysis, and NIST did a lot of this initial work on this effort. And around that time, as I said, a lot of work on graphical models, and so we had a lot of interesting work on multimodal asynchronous HMM, and then extension of that for conditional random field. But the main purpose of this tutorial today, don't worry, it is about deep learning. So we are going to look we're going to look from 2010 to 2016. But the reason I did this historical view is so that you don't believe that what I'm going to talk about is the only approach of multimodal. It's really just the last 5 years of multimodal. And you can see a lot happen in the last 5 years, and that's really exciting for that. Why multimodal became so popular in the last few years? Any idea why? Part of the reason is this community, and part of the reason is the computer vision community. So, why would you think? So one of the reasons is that if you think about human communication, words and images and speech signals are fundamentally really different from a granularity and from a representation perspective. At least up to 7 or 8 years ago, it was the case. Often language will be looked as a symbol, like words, and we'll also look about a representation, one-hot representation, or a lot of interesting feature engineering. And then suddenly this idea of distributional hypothesis, better known these days with the instantiation of Word2Vec, was a way to bring words into the domain of a digital numerical representation. There's pros and cons with distributional hypothesis representation. Since then there have been extension, character level language models. There's a lot of interesting extension. But what happened at that point is suddenly it's no more discrete symbols, but you got a nice numerical representation. But the real reason I think why multimodal finally got in is computer vision was so behind. If you think of 2000, were there any real computer vision system that worked at a level of real time that you could put in an application? There were really few of them. Face detection was maybe one of them. That's 2000. Paul Viola and Mike Jones did some wonderful work. But there was a lot of needed to go from that highly dimensional image representation to something that summarizes it. And the landmark work looking at ImageNet and doing these convolutional representation of images really brought computer vision to a level which, suddenly we have a high level representation. Again, it's debatable how much information is there, but there's definitely a higher representation, more compact representation. So, and during this time, people in speech were just waiting for everybody else. We're like, hey, we have already really beautiful, meaningful representation. We're just waiting for you guys to come in. So, language and computer vision, all three of them suddenly have nice numerical representation. We can start doing multimodal representation. So this is what we're going to focus on today in this tutorial. There is also the second aspect of this, which is more data came in. And this is one thing, a lot of the students these days, they're like, oh, I'm going to do research, I'm just going to download someone else's data set and just use it for my research. You have to think of how much effort is put behind these landmark and benchmark data set, and we have to value this very much as a community. And from a human behavior analysis, audiovisual emotion challenge, and MOTW example of that, the one when people think of language and vision, probably think of MS Coco image captioning. We had some effort in Germany and in Montreal for video captioning, visual question answering, and now these days people are becoming more and more imaginative on the kind of application, storytelling. There's a lot of spin-off from this work. When I teach this course, I always give people 4 main type of application for multimodal. Affect recognition is one field. If you want to know about this work, you should go to ACCI, Affective Computing Conference, or ICMI. The media description, which is somewhere in between CVPR and ACL or these communities, is a lot of work on image captioning, visual captioning. Event recognition is a subset of which I like very much, but was usually only computer vision. But when you start looking at multimedia or multimodal event, and so ACM multimedia retrieval. So these are the kind of applications you can see. Now, from the core of this tutorial is the idea that multimodal has 5 main challenges. There may be more, but these are definitely 5 of the challenges we need to solve as a community to do that. The 5 challenges are representation, alignment, fusion, translation, and co-learning. And if you want to fall asleep really well tonight, download this beautiful paper. It's, I think, 26 pages of the review of all the work. It took 2 years to write this paper, so, and I have to thank my postdoc Tadas for his hard work. But the core of it is to identify not just the 5 core challenges, but also define a taxonomy of this kind of work, so that when we talk to each other, we will know what is the different type of work and subclasses of work, so we use the same term. Now, when you read the paper and when you listen to the presentation today, and you're like, hey, I don't agree with this term, great. If you don't agree, please share with me your thoughts in a constructive way, not destructive. If I did not cite you, you can always email me. I will do my best to apologize in advance that I did not cite your work. We've done our best to include. But the main thing is the taxonomy that I think is, as a community, we need to define if you want to build the multimodal community. So today I'm going to do right now an explanation of these 5 main challenges before going into some more details. How are you doing right now? Shaking? Yeah? Wake up? Okay? Great. Perfect. So, and by the way, these challenges are non-exclusive. Most application will use a subset of these to be solved, to solve a problem. And we'll go example in a little bit. The first one is representation. And that's probably the one you know the most, because these days it's hard to do deep learning without thinking about representation. This is a beautiful way of thinking of deep learning. Yoshua Bengio had a landmark paper about representation learning. But so definition of representation in the case of multimodal is learning how to represent and summarize multimodal data in a way that exploits complementarity and redundancy. Now, there are 2 types of classes of work in multimodal representation. The first one is joint representation. And this is maybe the one that is the most intuitive. Joint representation is the idea of learning this one representation that is where both modalities will live. Both modalities will live in that representation. And so an example of that would be a representation where we have the word "I like it," a facial expression of someone somehow happy or surprised, I don't know, or joyful tone. All 3 of them living in a similar part of the space, where we'll have someone with a tense voice or depressed facial expression, and the same way we have, you don't use yellow on top of white, but yeah, wow, and a surprised facial expression, all living in the same space. So the advantage of a joint representation is that you have one place where everything is living, okay? And so you can take any snippet of audio and encode it in such a way that it will be similar to how you will encode language. So a lot of advantages there. There's some disadvantage which I will mention in a bit, but joint multimodal representation was some of the initial work on multimodal representation, where you will learn a visual, verbal representation, like say an image, how to encode an image, how to encode the description of that image, and eventually learning a multimodal representation. And so some of the initial work on audio-visual speech recognition, image captioning, even emotion recognition, all use this representation. And when you do this, or something similar to that, you're able to start doing what is probably one of the most surprising results from my perspective. This is the result from Ruslan on this, which was looking at vector space arithmetic. And I will explain this image in a second. What happens is you learn a representation of images, and a representation of language that are joined or very close to each other. And then you start doing arithmetic in such a way that you take an image, example of a blue car, and then encode it, and then you take the word blue, and then encode it, and then the word red, and encode it, and then do arithmetic. Blue car image minus blue plus red give me an encoding, and then I can start sampling from there. And if I start sampling from there, what other kind of images that come is a red car. Is it not cool? I thought it was cool. It was really exciting. Now, and it works also for some other words. So minus day plus night, minus flying plus sailing, minus ball plus box. There's a longer discussion about the failure cases, because these are the success cases. There's failure cases. The bottom line is these two words need to come in, if you look at it from a Wikipedia perspective, need to happen about as often, both of them. That's one of the aspects. There's other aspect of this to make it happen. Doesn't work always. If you do minus blue plus night, you're going to get some really interesting things. So don't do this. But no, there's a lot, but that was already really exciting. So language and images can live together. NLP, ACL, and CVPR can live together. Yes, I believe so. By the way, this was not true in 2008. CVPR and ACL did not live together really well. The reason for that I know is because they're completely overlapping the dates of CVPR and ACL in 2008, making it really challenging to do both. This year it was great. So joint representation is one. But the second type, which I personally like very much, is coordinated representation. Coordinated representation is the following. I will give an example in a second. But coordinated representation means that you have a representation in one modality, like language and visual, but you're not forcing them to live in the same space, but you emphasize them to be coordinated in some way. So language will have its own representation, but will be coordinated in a visual representation. I will give you an example, but before that, so let me ask you, if you learn independently a language representation and learn independently a visual representation, is there any mapping between the first dimension of a linguistic, like word-to-vec representation, and the first dimension of a visual representation, like CNN? There's nothing that forces it to be relevant. First dimension doesn't represent anything similar to the first dimension of the visual. So coordinating will mean so that each dimension are at least coordinated. They don't need to be the same, but they're at least coordinated so that I can start bringing these closer to each other. And a great example for that is using CCA, or canonical correlation analysis. I will give more details later in the tutorial, but the idea here is that you will learn, and this is just for one dimension, and we'll repeat it over and over, but you will say, hey, the first dimension for language has to be highly correlated with the first dimension with visual representation. And so you will learn a representation not just of image, but this correlated representation. And you will do it, and then for the second one, you will have it also correlated, but orthogonal to the first representation. In the same way. That's what CCA in a nutshell. If I look at it visually, this is my image representation, this is my language representation. And you're not forcing them to be equal, but you're saying, hey, this is the dimension where, this is the direction which is the most correlated with the other modality. And so this is going to be my first dimension. And there's some mathematics that I will explain to make it so that it's orthogonal, the second and the third. So this is a great representation. It's a pain in the neck to optimize right now. And that's why maybe it's not as popular as other ones. But I think fundamentally, I think it's a better way of representing, because the joint representation forces you, in fact, the joint representation, if you don't want to lose any information, there's something in speech that's really specific to speech. And forcing it to go in that joint representation mostly means that the joint representation has to do many tasks. It has to keep the fundamental aspect of each modality as well as the commonality. And so that brings an interesting question of what is the best way of representing. The second challenge is alignment. And this is in itself a very strong example of what multimodal is about. The idea of identifying the direct relation between sub-elements from two or more modalities. In a pictorial way, you have the one modality, let's say words, and then you have another modality, image, and you want to align the words with subpart of the image. That's an example of that. That's explicit alignment. Implicit alignment means I have another task, image captioning. And that's my task. My loss function is about image captioning. It's not about alignment. But internally, to solve that task of translation, going from image to text, I will internally, like a latent process, doing the alignment. So there's two different. One, I have a loss function that is directly about alignment. And second is the loss function is another indirect task, but internally I do the alignment. A great example of that is attention model, which I will describe in a second. But in explicit alignment, this is an example where implicit alignment, where I have a task of doing image captioning. So given this image, a dog with a tennis ball and swimming in murky water. So internally, to solve this problem, I will also do internally this task of alignment. Aligning either noun phrases or directly nouns, or in fact verbs some cases, with specific part of the image. This is an example of implicit alignment, and these days this implicit alignment is often due to attention. And I will describe more later, but just to give an overview, is I have an image, and I want to do image captioning. I want to find a caption. So what will I do? I will take the image, and based on the current image, I will look at and try to predict. Oh, sorry, the animation goes faster than I expected, but the idea is that you predict the first word, and before predicting the second word, you're going to look back at the image. Where in the image should I focus next? And then decide to generate the second word. And then go back and forth like this every time that you are about to generate the caption next word, using the language model. So this part is your language model, but then you're adding the attention into it. And what is beautiful with this, and I will have a larger version of that same image a little bit later, but as you go along, it starts focusing. I don't even see it. I forgot it was the caption for that. Oh my gosh. Okay, I will have a larger version of that a little bit later in the. So now you have to stay to find out what is this caption. So this is the second. The third one is fusion. And if you think of multimodal, anybody who's done multimodal probably heard the term early or late fusion. This was up to like 6 years ago, when people were doing multimodal, they were doing this model agnostic fusion. Model agnostic is, it doesn't really matter what's in this classifier. It really does not matter. There's these two fundamental ways of fusing information. Before I go further into describing that, I want to discuss what fusion is and how, from my perspective, it is different from representation, although really related to representation when you do deep learning. But fusion is about to join information from two or more modalities to perform a prediction task. And that is the fundamental difference. If you look at it from a neural network perspective, the beginning is really about representation, but when I get closer to the prediction task, that's when you're closer to fusion. And while in neural network, representation and fusion are really, there's a really of a gray zone, in certain cases, the fusion is very specific to the model. So example of that is SVM, Support Vector Machine, has wonderful extension to that, which is called multi-kernel learning. So a kernel, in the 10-second explanation of what a kernel is, I know if you any grad student in the 2000 knows what a SVM is. These days we don't always use SVM, but support vector machine, a kernel, is kind of a similarity metric. Okay, it's telling you if you have two elements how similar they are to each other in a high-dimensional space. That's often how you will do it. The multi-kernel learning allow you to have a different way of comparing audio segments, then text segment, then visual segment, because you have a different kernel for each of them. A different kernel allows you to model the noise of each modalities in a different way. So this is an example of multi-kernel learning of a multimodal fusion approach. And I still like graphical models. And so there's a lot of interesting work about using graphical model and random variable to represent and fuse information. Multimodal graphical models are also often based on latent variable. Latent variable, if you think of a latent variable in a model, think of clustering. Okay? That's the intuition I will give most people. When you think of an HMM, what is that latent variable really doing? It's mostly clustering your observation. In a really simplistic manner, they're doing it with a mixture of Gaussian. So latent variables are a wonderful way of summarizing and grouping word observation for you. So if you have a problem where you think that you want to cluster or group things, start looking again at latent variable and graphical models. Okay, the fourth one is translation. Translation is the idea of going from one modality to another modality. This is probably the one you thought the most about recently with image captioning. The process of changing data from one modality to another, where the translation relationship can often be open-ended or subjective. Anybody working on machine translation? Okay. You know the challenge of evaluation. Yeah, that's the same in multimodal translation. The same challenge that you find in evaluating good translation from one language to another, we have the similar challenges when we look at translation from one modality to another. So there are two different ways of looking at translations. One is example-based, and the second one is model-driven. If I had to give other names to that, that will also be non-parametric and parametric models. The example-based is often related to all of the work on multimedia retrieval. I have a query, and I want to get an image out of it. And how will I do that? I'll have a huge data set from Google or from Microsoft, and I look at example-based. I have this huge, and then it's a non-parametric approach. Either the simplest version of this is k-nearest neighbor version of that. So you have a bunch of paired data, and then you just look at the closest one and then retrieve from that. While the model-based will mostly look at a model, parametric model that is summarizing the task of translation, and then you use that translation model during the translation task. I want to show this example because often people think of translation from image to caption, but there's also the idea of translating from transcript and audio stream to visual gesture. It's called visual animation or visual puppetry. The idea here is I take this video, this movie, and only keep the audio track with the transcription, only this. And then I want to animate two types of gestures. Speaker gestures. Speaker gesture is a direct mapping of what I'm saying to the facial expression and the gesture of the character. And then you have the listener gestures. Listener gestures are harder because it's not just based on the audio, it's based on the fact that someone is listening to that audio. It's a listening task. So it's a dyadic or interpersonal dynamics. So let's look at so everything you see here, the appearance of the virtual character are handmade, but all of the visual gesture will be automatically processed from the audio track. Okay.
You snotty little bastard.
Your Honor, I'd like to ask for a recess.
I'd like an answer to the question, Judge.
The court will wait for an answer.
If Lieutenant Kendrick gave an order that Santiago wasn't to be touched, then why did he have to be transferred? Colonel, Lieutenant Kendrick ordered the code red, didn't he? Because that's what you told Lieutenant Kendrick to do.
Object! When you went back, you cut these guys loose! Your Honor, you watched us inside a body train! Your Honor, you doctored the logbook! Damn it, you coerced the doctor!
See yourself if you can.
Colonel Jessup, did you order the code red?
You don't have to answer that question.
I'll answer the question. You want answers? I think I'm entitled.
You want answers? I want the truth! You can't handle the truth!
I like that line very much. This was work of Stacy Marcella at ICT. He's at Northeastern now. This is great work, example of translation going from one modality to another. And you can imagine with all of the virtual reality, VR, augmented reality, this becomes even more important at creating characters. The fifth one is co-learning. Co-learning is probably the challenge you've not thought about directly, but co-learning is really exciting, new, or somewhat new approach. The idea of co-learning is transfer knowledge between modality, including representation and predictive model. Another term is, I have a task in one modality. I have a prediction task in one modality. Let's say object recognition. I want to do object recognition. And I'm plateauing. I'm not recognizing. I'm having a problem to generalize to new objects that are not part of ImageNet, for example. Then what I do is I go to my neighbor, my NLP friend, and then he says, oh, but we have a lot of knowledge from language about words and how objects appear and relationship between objects. Maybe we can use this to help to your task. So what it is you use one modality, language, to help the prediction task in another modality. And that was really great because that enables some zero-shot learning. So being able to recognize a new object you've never seen in your training set because you know that it has some relationship to other objects you've seen in your training set. And you know that because you've looked at a language either through WordNet or some other resources through language. There are three different types of co-learning. There's one co-learning where you directly have parallel data in between modalities. Or sometimes you have non-parallel data, which means only at a group level you have interaction between that, and then you have the hybrid version of that. So this is a summary of, and if you have one slide, this is the slide, or read the whole paper. But this is the taxonomy of multimodal research. The taxonomy of multimodal research with the representation, translation, alignment, fusion, and co-learning. For each of them, I presented right now the high-level classes, like joint and coordinated. But for each of them, you have subclasses that are also really important. Now what I will do is, through the tutorial, is walk you specifically through representation, alignment, and fusion, and go in more details, give you example and mathematical representation of that. At this point, this is a good time. If you're a little bit fuzzy, you have some question, this is a good time to ask questions. This is the end of the introduction, and we're about to get into some math about it. Yes?
Yes, for the representation, you talk about joint coordinated. So in your experience, which model actually tends to perform better than joint?
So,
and what are the rule of thumbs?
If I have a student starting on a project, I will start with joint representation, and primarily because of optimization. Currently, the way the coordinated representation are optimized is time-consuming and requires quite a bit of hoops to go through to get a good coordinated representation. So often, you start with a joint representation, but I believe that moving forward, people are going to coordinate it, or I've not seen yet, but I'm expecting really soon a hybrid representation. It's a representation, it's kind of a joint representation where part of the joint space is really joined and part of it is individual modalities explicitly modeled. So there's definitely some hybrid that's going to happen. But right now, if you have to start somewhere, I will start with the joint for the easiness of optimizing it, but fundamentally I like coordinated. There's something about coordinating that let each modality live in its own space, but allow to coordination. But we need better way of coordinating and also better way of optimizing them. Any more questions? Yes?
I'm not sure if I understand what's the difference between joint and coordinated representation, because I'm thinking that the learned joint distribution kind of reach to a coordinate distribution representation too by seeing each neuron has effect on the specific neuron. So basically go back and top down and see each neuron fires and then kind of find which between two modalities each neuron are kind of correlated with each other. I'm not sure if
I'm not sure.
So basically, I'm going from top to down and see. It's like when we want to find in image, for using attention, kind of, who is affected each neuron mostly, kind of say how they correlate to each other.
I'm not sure because you're bringing attention, which is a slightly different mechanism. And there's another example I'm going to give later of coordinated, where with autoencoder. So you have a multimodal autoencoder, and the easy way to think of a multimodal autoencoder is that a joint version of an autoencoder is really going to be a hourglass that forces everything to be in one joint representation, each modality joint represented, and then regenerate. The coordinated version will never force both of them to be exactly in the same joint space. It will allow for freedom, each of them to be in their own space for the autoencoders, but you need some coordination. And coordination, right now the best example is CCA, but it's only one view, and I think there's a lot more to be done. You could imagine some other way of constraining the two spaces to be coordinated, maybe to some attention. I have not seen that yet. Maybe the coordination could be so attention. But each of the modality live in its own space. That's the simplest view of that. I'm happy during the break or afterward to go in more details. Okay, yes, in the back and then in the front, yeah.
I got a hard time because we talked about lexicons and how we really want to understand which word really means what.
Yeah.
So for me it was a bit hard to distinguish between fusion and representation. As I said, also that's a gray area. Because for example, L diffusion can be kind of also a joint representation in a simple way. So can we come to an agreement of when we use which word, or would it be like representation is mostly a new word that connected to deep learning, but the fusion is kind of older approaches, or either any more distinguishable?
Yeah, that's a really good question. So yeah, the way I describe the simplest early fusion is to concatenate, do some PCA. That's the simplest way of doing a joint representation. So joint early representation and early fusion are similar. So I don't like the terms early and late fusion. We almost didn't even put them in that survey. We put them because that was used before. The best way I think about it is fusion is about the prediction task. Is specific about the task, the loss function you have in mind. And so if you are looking at a representation, a neural network, it will be closer to the loss function. But in neural networks, often this is just done through softmax or really simple. The loss function is very, the last few layers are really simple. And most of the work is done in the representation. But there are algorithms that are really about the classification task. If you think of a support vector machine, It's really looking at the boundary. It's a prediction task, like that hyperplane that separates the two spaces. And so when you build a taxonomy of different approaches, you cannot take SVM and put it with representation learning, although you could say kernel are a little bit of a representation learning. But really SVM and the extension of multiple kernel learning is really closer to the classification task. So we decided for the purpose of this that Fusion will be used as the final part of closer to the prediction task when you're ready to do the classification. And for a lot of the graphical models is also true. A lot of the CRF, conditional random field, multi-view CRF, it's about the prediction. So for these cases, it's clear. For a neural network, it's not clear where the representation in Fusion, but in my mind, Fusion is really closer to the prediction task. At least that's how we, you could say arbitrarily, decided that Fusion is that term, which is slightly different from how it was used for early and late Fusion. But we still, if you look closely, they're also classification tasks. Early Fusion and late Fusion are about this classifier, either jointly you concatenate the input for early Fusion or for late Fusion. So that's how we did it. I would love to discuss the taxonomy afterward also. You had one more question? Yeah.
Yeah, a quick one.
Yeah.
I think it could fall under alignment, but you didn't mention about the different regularities of the different modalities.
Yeah.
So when you're using text, it could be your unit could be a word, could be a character, it could be a morpheme. When you're dealing with images, you have the spatial dimension. When you're dealing with videos, you have an additional temporal dimension. And how to it could fall under alignment, but how to make it work, how to deal with regularities across different modalities and different tasks.
I love that. So different granularities. So I speak about, 3 words per second, 4 words. I speak quite fast, so maybe a little bit more. But about 3 or 4 words per second. But if you look at how we sample audio, it's a lot faster. It can be 6,000 hertz. Images 30 frames per second. So how do you bring these different the granularity? We put it in alignment, but there's the problem of granularity, or also I would say segmentation. It's a little bit relevant to that, is segmentation, and it's really important in audio, but also in video. And that's one place that's really, when we start looking at video, is looking at sub-events or communicative act in videos. You want to know how many frames before you start summarizing and representing that sub-event. And that is a mix, in fact, of alignment and representation. So what you're describing as the problem of granularity is a mix of alignment, but in the sense of segmentation, and it's a problem of representation. And I think this is the place, if you ask me moving forward, where I hope to see a lot more research. What I want is, I want an unsegmented stream of audio, video, and words, and I want you to be able to automatically find relevant segments and find a way to represent these sub-segments and jointly, it is a beautiful architecture you probably start putting in your mind of all this. So I think this is going to be a merge of alignment. We thought about calling it segmentation also, /segmentation. It fits there, but segmentation and representation together. Yeah, good. Okay, so as I mentioned, oops, sorry for the pixelization, each application is often solved with more than one challenge. It's not one fits all. It's not like I will solve emotion recognition simply by solving representation. It's often through many different, so emotion, media description is a representation, but media description is often a translation problem, so this is all together. So, whoops, basic concept. So I will spend about half an hour, 20 minutes just to get everybody on the same page. Some of it may be things you already know. Just to be sure, what's the difference between a score function and a loss function? Okay, yeah?
Loss, you want to minimize it?
Yeah, oh, the score is the output of your prediction. So your y hat or y, and then the loss function is how you want to optimize. It's going to be okay. So let me explain with the difference between the score and the loss function, so we're all on the same page. But when you are a different task, this simple. By the way, I use the example of linear classifier because a neural network is not far from a linear classifier. It with a little nonlinearity at the end. But to understand how to build a linear classifier, then you learn how to build most neural networks. And so the score function, the loss function, and the optimization are the three main tasks in a linear classifier and in a neural network. So the score function, is the idea of I have an image, I learn a model, and for each of these different class labels, I will give a prediction score. Okay? So how likely is it that we're a dog? How likely a cat, a dog? If it's a neural network, it may be just the softmax output. So a linear classifier will do this in a very simple manner where you have your input. So input is maybe this image, 32 by 32 pixels. And then you will have the weight, which does the linear mapping between the image and the score function. And sometimes or often you'll have a bias term. So these are called parameters, W and the bias. So the weight and the bias are your parameters. And then you have your class score. Your class score is your output of your classifier or output of your prediction models. So if we have an image of 32 by 32 and 3 colors, that's where the 3, then you have 3072, that's the dimensionality here. If you have 10 labels here, what would be the dimension of W? Just to be sure you follow, 10 times 3000, and then you'll have your bias, which is one bias for each label. You could almost see it as a prior, although it's not a probabilistic framework, but it is a little bit like a prior. And then the class score will also be 10 total. So linear classifier, if you look at it from a space perspective, it is really learning that hyperplane that differentiates the two classes. This is for the binary case. And the score is really looking at this distance between the plane and the hyperplane. This is between the element observation and the hyperplane. And you do that just a notation tricks because you're going to use that. Sometimes you see nicely explained like this, but people often look and will do a small trick, which is put the bias directly in the weight. It's just a simple notation trick. This is just adding 1 into the observation. Another notation trick that people do is these, instead of being really, if you have multiple classifiers, one for dog, for cat, for birds, you often end up having weights and bias for each of them. You can also simply notify this simple change of notation to change that, and then if you don't have explicit naming of your label, you can just put a simple index like J. So this is just some notation trick. What I wanted to say is I want to get back to the loss function. So the difference between the score and the loss function, the score is what you get from your model, your parametric model. You get the score for each label. That's what a multi-class problem will do. The loss function, and that's, let's say the label is Y. So this is my score. This is my label. The loss function will tell you how good of a match is this. How good are these numbers? And I force you to give me one number telling me how good these scores are. That's what the loss function is doing. The loss function is how to assign only one number representing how unhappy, which is, as you mentioned, minimizing. You could do how happy you are, which is maximizing, but people seem to be more unhappy, so we minimize. How unhappy you are about the score, okay? So this is what the loss function is doing. The loss quantifies the amount by which the prediction score deviates from the actual values. I know it sounds like this is basic, but just keep that in mind, because when you read papers, you're like, oh, there's a score function, there's a loss function. These terms just to be all on the same page. How to normalize the score? Because that's a problem. You have all these scores, and you want to get only one number. So how do you normalize these scores? There's different loss functions. I'm only going to highlight 2 of them. There's a lot more. In fact, there's some even created every day. But there's some that are basic. And cross-entropy loss is probably the most well-known from that. In fact, cross-entropy loss is mostly a logistic function. Where if you think about it, you have these values that goes from, the score can almost go from -infinity to +infinity. Every time you hear, oh, I have in -infinity, +infinity, and I want to normalize it between 0 and 1, you should start thinking that it's going to be something close to a logistic function. The logistic function does this for you. From -infinity to +infinity, that's going to do a nice normalization for you. So the cross-entropy loss is really just doing this, taking all these core functions and normalizing them. In fact, if you had only one class, then it's directly, or 2 class being dog, no dog, it will be directly a log, the cross-entropy loss will be, in fact, a logistic function. But if you have multiple, then it becomes more of a softmax. And that's what you've seen more often. The softmax is just a generalization of the logistic function for multiple label or multiple class. The cross-entropy loss goes a little bit further than just the soft. So what do? I got here, these are my score. Okay? And I just normalize it with a softmax function. And then I will just do a simple thing to be, because softmax just does normalization. It's still a happy loss function if I was to use it. I want to make it unhappy, so I will do the minus the log, and that's what the cross-entropy does. The cross-entropy is mostly a softmax that minimizes the negative of the log likelihood. Okay, just a simplistic ways. Sometimes you see these really fancy. There's a mathematical aspect of it, of looking at it from an entropy perspective, but I don't have time to go in the details, but this is a nice intuitive way of looking at cross-entropy. The other one I want to at least give an intuition is the hinge loss, which probably if you were doing research in the 2000s, you will have called the SVM loss. But the hinge loss these days, or max margin loss also. And the hinge loss, so given an example I, the hinge loss, what it looks is that the difference between the correct class scores and the incorrect class score. Okay? So you will look at this different, it's easier to look at it here. So what you want is if the class score is correct, you ignore that. In fact, anything that's well properly predicted, they're not going to affect. What it is every time you are, or every time you do a mistake, then you're going to start summing these mistakes. And then there is a small aspect of the hinge, which is just how much of a mistake do you need to be accepted as part of the summation. And so the hinge loss, mathematically, if you have the scores, this is the score, how much you think it's a cat, how much you think it's a dog, how much you think it's a bird. And in this case, you will see is, if you know, for example, that this is a dog, which is the first one, and then you can look at it given the log, and that will give you the simple summation there of all the mistakes you've done in this. So this is the hinge loss. There is one more aspect I want to talk about for loss function. In fact, a real loss function usually has 3 components. The loss function that I just described, regularization, and sometimes you also have other constraints. And in the case of CCA, I will show what are these constraints. But regularization is the idea that if you don't have enough data, and I know these days, we have so much data, our regularization is quite simple, but we're still doing regularization. How many of you use Dropout? dropout is a type of regularization as well. So regularization can be, at least in the old ways, can be done either through L2 or L1 normalization. L2 is the one that will emphasize or allow you to recognize something even if you've not observed it or observed it really few times. That's the L2 norm. The L1 is great because it forces it, because of its shape. If it's either really small, it would force it to be 0. And otherwise it will allow this dimension to be there. And this is why often all of the sparse representation use L1 norms. This is a short representation of the linear classifier. Now, hopefully now you know what the score function is, what the loss function is, and just a quick aspect on optimization. Neural networks. We call them neural networks, but I will say these days the neural networks we're using don't really look a lot like a neuron anymore. If you look at ReLU function, all these activation functions, they start looking less and less like a neuron. But they were originally inspired from neurons, as you probably know, where we have the axon that brings you all the input, the synapse, and then the activation function coming out at the end that decides after enough evidences, eventually you start activating. The neural network is really close to a linear classifier. And that's what I want to make the link with that. In fact, neural network is a lot like linear classifier, but then I add on top of it an activation function which brings the nonlinearity. So all of the things we talk about, loss function, score function, everything is true also for neural network. We have your input, you have the weights, and then you have your activation function. Activation function, you have different type of activation functions. In fact, I think there's probably a new one invented today. I'm sure one of you guys invented one. Okay, but there's a lot more coming. But the basic one, the basic two, I would like is sigmoid brings it between 0 and 1, and tan bring it between usually -1 and 1. And this is depending on your goal. Why sigmoid is so interesting? Sigmoid does it between 0 and 1. 0 and 1 is wonderful when you have an LSTM because it's going to do the gate for you. 0, I close the gate. 1, I open the gate. Okay? But if you have data that is between -infinity and +infinity, and you want to keep that range, don't go and put a sigmoid on it. You should put something more like a tanh, because you want to keep that negative and positive range. And that's why the LSTM, the first gate is a tanh, and then the, which is the input. But then, if you want to close and open some gates, then you use the sigmoid to open and close gates. But your data itself is you're not going to put a sigmoid on this. And so that's just, and the GRU has the same intuition as well. We'll go into more details a little bit later about this. The loss function, let me go. The multi-layer feed-forward is just a recursive approach on the same approach. So if you have multiple layers, then you have one layer that becomes the input of the other, and you simply do it from a recursive. So if I was to write it, this is almost a recursive way of writing my score function. I know these days you simply put it in either TensorFlow and don't realize that all this math is happening behind, but I believe that you should know a little bit because these scoring functions are important mostly when you start thinking, the loss function, when you start thinking about how to integrate other knowledge. How do you integrate other knowledge in your model? So the loss function, example here of an Euclidean loss function, is simply looking at here, now that I have the score, how do I decide if it's how unhappy I am? So it's one thing, remember, loss function, unhappy. That would probably be unhappy about my scores. That's what you should think about. Optimization, we want to find the minimum unhappy or the maximum happy of a generic function. how do you do this? You can search everywhere. That's the extreme version. Now these days, everybody do with gradient descent, gradient approach. The gradient, if you look at it from a mathematical perspective, it is the limit to the h being as small as possible, the delta h being as small as possible, looking at the gradient of that. So, gradient computation. How many of you manually wrote down the gradient of their model? How often do you do that? Write down the gradient, okay. No, otherwise Keras does it for you, huh? But no, the gradient is good. I like it. I do force my student to write at least a few times the gradient. Writing down the gradient of an LSTM is quite a lot of fun. But yeah, the one thing to know is backpropagation. Backpropagation, if you have to summarize backpropagation, the summary of backpropagation, chain rule. That's what backpropagation is. Backpropagation is just doing chain rule. It says, I want to compute the gradient of this whole function, and I know that there's some recursion in it. So I will use the chain rule to solve and compute the gradient. So if I want to compute the derivative of y, my score, given the input x, and I have this latent variable h, then the chain rule tells me that I have the first partial derivative dy dh and the second derivative of dh dx. This is the representation if I have a or variable that are only one dimension. But what if I have multiple neurons? Then I can extend that. It's called multipath chain rule. And really what it is, it's a simple summation. So you look at all these different neurons, and this is your score. And then if you have as an input vector, then you are in fact extending that for each of them. So you have the derivative given your first dimension of x1, you have it for the x2 and then for the x3. Now, I will do magic, and I will take all of this equation and summarize it in one equation in a vector representation, which is represented here. And so this is the gradient representation, and this is the equation for backpropagation. Okay? This is one equation I want you to remember for backpropagation, and it has two things in it. Okay? The first thing is called local Jacobian. And the second one is the backpropagation gradient. This is simple. It has only two parts. When you do backpropagation, you always start from the top, and you backpropagate your gradient. And at every step, you're going to take whatever you backpropagated up to now, and you add to it your local Jacobian. Your local Jacobian is your local change of the gradient locally in that. Jacobian is just you could see it a vectoral representation for the gradients. Let me do it in a better, more interesting. Okay, this is your multi-layer perceptron. You should recognize it. So this is my observation. This is my first layer of neurons, second layer of neurons. What is this? Z. Let's be sure you're following.
Scoring function?
Yeah, great. Scoring function. Thank you. Y is my ground truth label, and I use my ground truth label and my score function to get my loss function. Okay? That's just the basic one. So the backpropagation, you start from the top. Backpropagation starts from the top. So, you do first a forward pass. The forward pass is you simply propagate your information. It's easy because I have all the equation here. How do I compute H1? It's easy. I already have my W, and so I simply propagate this information moving forward. The interesting part is the backpropagation. You initialize your gradient with 1, and then you compute the local Jacobian. The local Jacobian for this representation. So it will be the Jacobian, the derivative of the loss with respect of Z. The derivative of the loss with respect to Z. That's more local Jacobian. And then you use the chain rule. The backpropagated gradient, which is 1, that's what we started, times the local Jacobian, dl dz, that become a new gradient. And then I repeat. So that I have my gradient here, and I want to get that gradient, dl dh, and I simply do again the chain rule. And I do the chain rule over and over until I reach the x. So backpropagation can be used in many different approaches. These days we use the simplest one, gradient descent, but I will highly suggest to you use the second order approaches like quasi-Newton. These are, yes, more demanding, but they're also more powerful if you have a small model. Parameter updating, this is one of my last equation for optimization. This is the typical optimization. So I have my current optimization, I don't have the figure here. Optimization is a little bit like walking in Switzerland. Okay? And I take this from Carpati, so I stole that intuition. But it's walking in Switzerland blindfolded. That is, but I want to find the smallest valley in Switzerland. And I start somewhere in one of these mountains. And so I want to find the smallest valley. So what I do, I compute the gradient. What do? I check in a little bit there. I check on the right. Okay, that's going down both ways. I'm going to step in the middle of where the gradient is going. That's what gradient descent is doing. A blindfolding exploration of the gradient and then taking a step. Now the question is, how big of a step should I take? Gradient descent, the vanilla one, takes a full step. The idea is sometimes you would like to look at the second order derivative to know how big of a step I should take. Because if I take too big of a step, I may going back and forth between two mountains. That's quite a big step, but you could imagine that. Okay? This is my previous estimate. This is my previous position. And I want to decide how much of a step. That's often called learning rate. And that gradient is me looking and trying how the slope is. And so there's been extension to that. You can decay over time. You start by taking big step and eventually take smaller step. And then these days there are a lot more extensions to that with momentum, Adagrad, Rames-Prop. They're just little ways of taking smaller and smaller steps. Okay, we're all on the same, we should be on the same ground mathematically. Any question right now about these linear classifier and representation? So, I think let's do a new survey. How many of you have used vision and visual representation in your research in the last 6 months? Okay, great. So for that reason, I want to go a little bit more details on two representation, visual and acoustic, because all of you should know about language. So visual representation, so back in the days, computer vision had a lot of work on different representations. We were looking at image gradient. From image gradient, we were looking at edge. Edges, in fact, were looked at in a histogram, so histogram of gradient, and optical flow. Gabor is really interesting, by the way. Gabor is a generalization of edge filters, and supposedly your eye is also using something like a Gabor filter to that. SIFT, there were so many of them. Now, I don't know how many of you were at CVPR, I know at least a few of you. We don't see them anymore. Everything is deep learning and deep representation. And so, here's my fundamental question to you. Why people in computer vision like CNN so much? Convolution neural network. Why are they not using... I give you the answer. Don't read the answer. Why not using MLP, multi-layer perceptron? Why a CNN? What's the advantage of CNN? Yeah.
Well, if you would force a parameter share within a filter.
Yes, exactly. Yeah, that's
parameters versus
Much less parameters, exactly. Much less parameters. CNN compared the same configuration, an MLP and a CNN. CNN will have a lot less parameters, and then it also takes advantage of the redundancy of the what we'll call often the kernels that will be learned. So these are the two main aspects. MLP connects multi-layer perceptron. If you were to do this, you'll have an image of, let's say, 32 by 32. This is a small image, huh? These days is 1,000 by 1,000 or even more. And then that's your first layer, is just this, okay? And so how do you go, and if you do it with an MLP, it's going to be very high number. In fact, if you look just 200 pixels, the first layer will already have 120,000 time n parameter, n being the number of kernel. One thing to think about is in computer vision, whether the CNN, the intuition I give people with the CNN is pattern matching. Okay? Pattern matching. What the CNN will do for you is look at little pattern. Pattern is a template. The simplest idea is little mouth corner if you to recognize a face. How do you recognize a face? There's some eye corner, there's some mouth corner. These are small templates. And this is something you will use in the CNN. I will give you in a second more intuition with that. But the other intuition behind CNN is the eye. At least, I don't know, okay. People who invented CNN didn't have that intuition. But now that we look at CNN, we're like, oh, that looks a lot like how the brain is also looking at it. And this is the idea that really early on in the brain, we look at small patterns. What are those small patterns? They're edges. The simplest V1 in the brain, or V2 in this level, is really, in fact, it's earlier than that. It's at the eye level. You will look at patterns like edges. And then from there, you look at edges, and then you've got to start looking at parts. And then from there, you're going to start looking at objects. So there's a hierarchy also that you want to learn. So you want to learn very simple representation, and as you go up every layer, learn more and more complex. Whoops, sorry. So let me give you a tutorial in, usually they have, I have an hour and a half on convolutional neural networks. So I'm going to do it in 5 minutes. But ask questions if it's not clear. But it's really interesting how convolutional neural networks are developed. And this is an example, by the way, of convolution. Convolution is the idea of taking an image and I have what's called a kernel, okay? And I'm going to convolute. Convolute is just a fancy word for multiplication. Huh? Convolution, it's slightly, there is a flip of it, but if you think about, if you have to remember convolution, just think multiplication. I take this and I multiply it by this, take this, multiply by this, and that gives me that point, pixel. I take the same, multiply slightly by a next, and then I eventually get this response map. This is called a response map. So I use one kernel and get one response map. What will I do in a convolutional neural network? You've probably heard another really fancy term, tensor. Tensor is a lot just like a 3D matrix. It's really stacking together all of these response maps. One response map, that's a matrix, 2D matrix. I put another response map, another response map, another response map, I get a tensor. Tensor is the stacking of all my response map. Okay, really simplistic. I'm trying to use the term. Don't get angry at me, or mathematically it's not completely exact, but that's the intuition I like to give people for that. So if I was to stack them together, that would be my kernels, convolutional kernels. This would be my input, convolutional kernel, and this would be my tensor response map. Okay? So let's go from an MLP to a CNN. We're going to do a transformation. Okay? How do you transform a fully connected MLP, multi-layer perceptron? So one layer, this is the input, you recognize the weight, and then you have your activation function. How do I transform this to be a CNN? First step, remove the activation. Okay? There's no more activation function. You can have other layers, but by default, the CNN, the first layer of convolution, doesn't have the activation function. Okay? So now what do we have? We have different outputs, W. We have different kernel, W1, W2, W3. But these kernels right now are really high dimensional. Okay? In this case, one kernel is a full image. But what did I show you earlier? The kernels are really small in this case. So I want to have small kernels. What will I do is I will drop most of these links and make W extremely sparse. This is where I win the number of parameters. I make W very sparse. In fact, every input is going to be accessed by only a small subset of kernels. And the last one is to tie weights. You will tie some weights here. And tie the weights means that you know when you do convolution, you move things around. Okay? You convolute, you take your template, and you repeat it over and over and over. You want, if you repeat things over and over, you want that when you multiply that template, you want the weights to be the same as if you were to do it and that part of the image as the same as if you're doing in this part of the image. So what you do is you say, hey, I want to multiply my kernel by the image and I want to have it in the same kernel repeated over and over, so I'm going to tie the weights. So I did two things to reduce dimension. I made it more sparse by having very small kernel. And second thing is I made it because I want to have the same thing as a convolution. And this is just a trick because I want it to be extremely fast. One multiplication of W times X, and I have right away the output of the response map. Okay? So this is the trick to make a multi-layer perceptron a simple, very, very efficient way of taking an input, which is an image, and making it a response map. So if you wonder how to do the long way of implementing a convolution neural network, is to take every kernel and multiply it locally, but the CNN does it in one shot by multiplying the weight matrix. And so this is what the weight matrix will look like, very sparse, and a lot of the weights will be tied together. So, and finally, the last trick from a CNN is the idea of pooling. And pooling is a wonderful word because it sounds different than what people were doing before. But really, pooling is a simple either max pooling or average pooling. And you see these networks, and then they're like, oh, and I have many words, and let's say I want to create a representation of a sentence. Okay? And then I have, let's say, a first network that give me word2vec for word 1, word2vec for word 2, word2vec for word 3, okay? You do this, and then I want a representation of the sentence. You could, in the old ways, just say, I average all of these vectors. That would be one way. The new way to say the same thing is I have a mean pooling layer. Mean pooling layer mostly means that I'm averaging all of them, okay? But a mean pooling layer will say I bring all of them together using a certain operator, either mean, max, or something. So I'm just rambling here. But yeah, pooling is this idea of reducing. And the reason we do the pooling is to bring the hierarchy that is needed in the representation. And so using that, you get representation like AlexNet, and you get some of these different representation. Acoustic, how many of you use vocal or speech? Okay, even a few of you? Okay, so acoustic representation, again, had a lot of representation before. Some of them, like the most famous MFCC, mel frequency, which is a little bit like fast Fourier transform with a small shift in the responses. But these days, there is 3 ways of looking at speech. One is raw signal, and we see some successes, a few success in raw signal, meaning you take the audio directly. A lot of the work often use spectrogram, and some of them also use features like audio features that were already used in the past, like MFCC. So we see work that use these 3 types of representation. Raw signal, as we mentioned, is really high sampling. Raw signal of audio, really high sampling rate. The time window will be simply the idea that I have this raw signal and I use a representation that will summarize locally with these thin slices. Spectrogram will take that thin slice of audio and compute the FFT, fast Fourier transform, to look at how much frequency is there. So low frequency, high frequency. And you can repeat this over time, and this is for one small window, and if you do it over a larger window, you can represent the spectrogram simply by stacking them together. By the way, this looks like an image, like a spectrogram, and it looks really tempting to use it as a CNN on top of that. That's really tempting. It's a spectrogram, okay? So it looks really tempting to do a CNN. If you do that, be careful, okay? Because the image, CNN, is designed for an image. And one end of the thing of a CNN is that it's translation invariant. Okay? And in this case, translation this way, I don't mind. You can have all the invariance you want. I am happy with it. But this way, this is not translation invariant. There's a huge difference. If you see the same pattern here or here, there's quite a bit of difference. They mean very different things. It's not just the mouth corner seeing a little bit higher or lower. This is not that. So be careful doing a CNN on spectrogram. Some people get results on that, but be careful when you do that. There's some interesting work, I forgot how they call it, but something like phase-based CNN, which mostly have CNN kernel dedicated to each part, like you split arbitrarily your spectrogram in 5 parts. But this is low frequency, high frequency, okay? So they're really different, and you don't want a pattern that you see in one to be really different from the other. Okay, this is me telling you to be careful with audio, and you can use these to be able to recognize words, so speech recognition, do emotion, and also voice quality. That's another aspect of that. Audio representation used to be also a lot through handcrafted features. Now these days you see more and more representation that are neural network based. And I would say speech was one of the first fields that embraced autoencoders. Although you see autoencoders for the modality, there were there were some really early results on autoencoder. So I want to give this about autoencoders. How many of you has used autoencoder in the last year? Okay, a larger number. So autoencoders, what's the idea? What does it mean first? It's from the Greek self. Oh yes, okay, great. I surprised you. Wow, I guess he knows Greek. Autoencoder, but the main idea is how can I learn a representation in such a way that I can use that representation to reproduce the input, okay? And the idea here is often these autoencoders will follow a kind of hourglass representation. So we go with high dimensional input, bring it to some kind of lower dimensional, but lower dimensional that keeps enough information to be able to recreate the initial and so you have 2 parts in it. You have the encoder, the F function, and you have the decoder, the G function here. And so encoder and decoder version. And then you have a really nice little extension of that. Where is it? The denoising autoencoder, which I thought was a really neat, I think it's folks in Montreal who had first version of that. But the idea is, instead of going ahead and directly using the input, which is now here, is I'm going to add noise on the input. And even with noise on the input, I still want to be able to recreate the same. So your loss function is really between the generated and the original, but the function, the encoder function does not work directly on the input, but works on the noisy version of the input. This is a nice extension of the denoising. It leads to more robustness, and the noise can be in speech by adding noise on it, but on images also. Will be about changing, shifting the image a little bit to make the model more robust. For language, I'm not sure how the denoising works. That will be anybody denoising? How do you add noise? You could probably change a few characters for fun. But this is one aspect of denoising. The stack denoising autoencoder is a deep version of this. And so you, instead of learning only one layer, you learn multiple layers. And what I like is that you usually learn these in a greedy fashion. So you learn a one-layer autoencoder, and then from that start learning a two-layer, and then from that you can learn a multi-layer autoencoder. So that's the stack autoencoder. So how is everybody? Because I'm about to start the fun stuff, which is the multimodal. How are you feeling? Shake a little bit? Are you ready for a little break? Okay, so let's take a little break, 20 minutes, and then we'll start the fun stuff about multimodal representation, alignment, and the translation. So you could say that these are still coordinated, but this is joined. That's what you're saying. That's interesting. Yeah. So okay, that's really be interesting. So you could imagine a model that does have kind of a joint layer, but at the time of using the representation, you don't use that joint layer, but you use the layer below that has been coordinated. That would be interesting. That would be a level of coordination. But when you use them, you would use these. If you use these, then yes, it follows. Yeah, that would be exactly. And you could, okay, and now I see what you mean. You could have this to be, and one thing is maybe this is attending to both, but this part isn't it. Yeah, that would be beautiful, yes. Yeah. What's your name? Okay. Where is Element AI? Sorry. Okay. Oh, cool. Donc tu parles français? Okay. Okay, but it's in Montreal? Okay, I'm from back in the day, my family is still in Quebec. Now I live in Pittsburgh, CMU. But I visited Yoshua a year ago, and Aaron and the whole family. So, how much interaction is there between Element AI and the group? Basically, the idea is now Okay, yeah. And is it full-time researchers, postdocs, or what's so basically okay.
second one are like students that like
Okay. Okay.
and the last thing is even out from the society.
Yeah.
They that
Oh, okay. Okay, so more basic research, applied research, and development. Okay, great. That's nice to. I've heard about that there was a spin-off, but I didn't know people. How many of you are here from elementary high? Okay.
there is one more to get beyond that because someone just sees it from the dolls.
Yeah. Okay.
Officially, I am only one that comes with the bags.
Okay, got it. Nice to meet you. Yeah, great to meet you. Okay, thank you. Bye. Hey, how are you? Yeah, nice to see you. Yeah. How is it for now? You're doing still a postdoc with and how is it going, the life as a postdoc?
It's going well. We have many
Yeah. What are you, did you change or is it the same? Are you working again similar topics as the PhD topics or is that something?
I have like a global
Yes? Oh, you started, okay. That's interesting. What kind of thing are you looking at? Ah, okay. Yeah. With Stefan, and we've done also now CMU with schizophrenia, also we're doing some, so it's great. Is Rita also here, or yeah, Rita, how say it? Hada, sorry, don't say it. Is she here also? No, are you presenting something?
Yes, I have a postdoc.
Okay, what topic?
It's the work on analyzing counseling situations.
Which kind of interaction?
Counseling.
Consulting interaction.
So we have these paper on counseling.
Yeah?
Yeah.
How did you undertake empathy?
We have these counseling sessions like something called division review.
Okay, yes.
Specific counseling. So we have expert counselors who can as you know, it's a pretty discussion. So it is difficult to get this counseling.
No, and the numbers are really small usually. How many interviews?
We have it for this where it's kind of a collection. So it's not still small.
Yeah, I mean, it's large from a clinical perspective. It's small from a machine learning perspective.
I will try to start with the then they said we cannot share. And it is a separate course side. We recently set up a session with
Yeah.
and people, I mean, there was some study stuff.
Yeah.
And the cancer research center.
It makes research really challenging in this field. We managed to share one data set, but we had to, we cannot give video in for the audio, we had to zero out, like remove some of the audio segments.
Right, that's what I did.
It's a lot of work to anonymize the data, but I think this is a good effort. If you can anonymize the problem is it's really hard to anonymize video.
So Because when it's study comes from the classes in it's more sexual education, and they say we are not allowed.
Oh, that's sad. There you can do full multimodal.
Yeah, and that's why when I saw you were doing
And you, because now you're second year postdoc?
Yes.
Are you gonna, what's the plan? Do you have
Well, actually, I was offered a research science position.
Oh, that's a good news.
Yeah,
Okay.
but I mean, we are still working on it, and then it's
Okay.
gonna application next sometime September.
Yeah.
But I'm still, I mean, I'm still busy, so,
I know, that's always the hard decision,
Yeah.
like at this point, is there's industry, there's research scientist position.
Yeah.
Okay, so you're still deciding on that? You're
yeah,
gonna
I
make-
mean, even though I've been hacking today's are mainly
the positions, yeah,
Yeah.
different. Yeah.
so it's, I mean, I enjoy research and it's much fun.
Yeah, and have you done some teaching during the postdoc? Or?
No, I've been learning since
Okay.
undergraduate, so I have students.
That's good.
Yeah,
Okay, that's
it's not like
really
formal teaching.
Yeah, no, and did Radha include you in some of the grant proposal writing?
Yes.
Okay,
I
yeah.
was, even last year, I was trying to do something.
Yeah?
It's quite fun.
That's great.
Yeah,
Okay.
not the best stuff, but we're still learning.
I mean, these are hard to get, but it's a good. From what I got is if you do get some funding from NIH, then there's a high likelihood of getting second time funding from NIH.
Yeah,
So once you get in the loop, then it's exactly. Okay. I was trying to stop by the poster. I think one of my students presenting during the same time, so if I don't see you, otherwise, nice to see you, Veronica. Yes, nice to see you. Hi. Yes. Oh, thank you. Not yet. There's a version of it for CVPR 2017. And I was debating with the I don't know where to put them if there's an official ACL website. Otherwise, what I would do is put it on my personal website. I think that's going to be the easiest. Yes, okay, thank you. I believe in, like, instead of making it complex, give a good intuition. So that's for the student. Okay, that's good because.
Especially because there's so many things to be tracked.
What's your main research interest?
Text association and summarization, but one of the things that I do is
Yeah.
audio.
Do you have some examples on that? Huh? Okay. Because, yeah. No. Yeah.
But you can imagine our conversations.
So, because we have the MOSI dataset, which is multimodal sentiment analysis, and we're building MOSI 2. And so it's going to be, we're shooting for larger. 30,000 utterances would be manually annotated, and we're going to all video line, all from YouTube videos. People love to explain and describe things, and then we're going to go further than sentiment. So we're going to look at basic emotion, arousal balance, but we also want to look at persuasion, what makes someone persuasive, confidence. So we're looking at a few speaker thread also. So I didn't realize that, I mean, not too surprising, but I didn't know who was the point of contact for that. But
How about I send you an email then?
it will be, yeah, Mozy 1 we can share right away, the annotations. But Mozy 2, and with the, maybe with a close collaboration, we can make a Mozy 2.5 or something like this. And Lighters. Okay, nice hacking, yes. Nice to meet you. What's CSIT? Yes. Okay. Okay. Yeah. Yeah. Yeah, so I kind of wanted to make I kind of forced something in, so I need a whiteboard. It's easier with a whiteboard. So let's think of an image and a 32 by 32 for now. And I have my kernels just 2 by 2. So what I really would like to do is get the output y. That's x, my image. And what x is my image, 32 by 32. And the output would be the response. Response meaning I want to multiply 4 by 4 times 4 by 4 and multiply everywhere and get that response. Now, one way to do it is to do manually multiply each of them and get that response. But what I would like one multiplication that will give me that exact same thing. And so you have to look at it mathematically, but that pixel, that response, that one, this is from that point to that one, has how many inputs to that pixel? 4. These 4 pixels. Okay. So that's the only thing I need is 4. So if you think of a multi-layer perceptron, usually that pixel, that neuron, will be connected to all 32 by 32. But now you don't want it to be connected to all 32 by 32. You only want that first 4. So, and the next one will be the next 4. So that's what the that's the first aspect of W. The second is that first neurons, which have the 4 by 4, the weights. There's weight for the first pixel. There's a weight for the second pixel. There's a weight for the third, and there's a weight for the fourth. So there's 4 weights. Now, if I look at the next one, they are going to be the exact same weights. So that's what I mean by tying the weights. And so when you eventually take that image and multiply by W, you're going to see this W being mostly zeros, and the W1, W2, W3, W4 will be repeated for each of them. So was it your question about how to do the convolution with just one matrix?
Yeah, that's right.
Yeah, so the way to do it, okay, now I see. So 32 by 32, in the example I did, is in fact I'm taking 32 by 32 and make it as a long vector. My image is a 1D vector, one-dimensional vector. That's my input, that's one of that dimension. So 32 times 32, I don't know, 2000. Now, W is going to be of size 2000 by the response map. Sorry, now I see the confusion because I put, yeah. So okay, it's a 2D image that I put as a vector, and the output is also a 2D image that I put as a vector. So the W is the size of this times the size of this. Yeah, the size of W, exactly. It's just that it's easier to think about a 2D image, but in fact I end up vectorializing the image. Yeah, and so if you have multiple kernels, either you see it as many W's, or W becomes a tensor, which mostly end up being, if it's a tensor, a 3D matrix. So a 2D matrix is one kernel, and if I want another kernel, is I have another matrix. If I stack all of them together, that's a 3D matrix, and that becomes a tensor. It's just a fancy word for 3D matrix. So if I have that, then my response map will be not just one, but I have many of them. Okay, no problem. Yeah, nice to see you. Yeah, you yeah? Yeah, I remember, yeah, so where are you coming to see? Where are you going finally?
I finally go to my post.
Yeah. That's where we're going to move forward is physiological steps of you say viable signal or wireless? Oh, wireless. Like Wi-Fi. Oh, no, I've never played with Wi-Fi. So, no, Wi-Fi. Oh, no, I've never played with that. Oh, that's interesting. No, the one I'm thinking is EEG and electrical.
It's a physical device.
Yeah, the two and it will have brain waves or things like this.
Yeah, but if you use wireless, no, you don't have to wear it. Without body contact.
Yeah. But I know they hear me well, but if it's for the recording, yeah, the people can hear me well. Okay, I would only wear it if the recording company needs it. Otherwise, I think you won't hear me. I would confirm to them at the beginning. I would keep it just in case. Okay, and it's just a turn on here. Okay, thank you. Okay, great. But no, I've not played with Wi-Fi, so that's going to be interesting to hear about your progress. Okay. Yeah. I love that. Okay, I'm good to hear that you're not too far. Boston is a nice place. Yeah. And I have nothing bad to say about it. I love the night to go.
I also have a non-crash.
Yeah, just okay, yeah, two more. Yeah, when we project them word oh yeah, okay, that's more this way. Yeah, that makes more sense. Yeah, then you just add the noise on the word representation. That makes more sense. I would be. That sounds true. Yeah, trivial. Now that you're saying it, sounds like a very trivial. Yeah. One I was thinking is also when you look at Twitter, people do mistakes when they spell. So you want to maybe also do noise that way. Spelling noise, but yeah. That's a good point. I don't know. Yeah. Yeah. And you want to know the noise, the way you want to add the noise in the word vectors, you want to be smart because it may not be all the linear aspects. Yeah. Yeah. But I will talk to you one later. Yeah. Thank you. Yeah, after the presentation, if you have questions. Let's discuss more after, because that should be published longer. I want to be sure to understand the problem, so I would be staying after the tomorrow. Okay, thank you. Okay, great. Everybody got their caffeine, coffee, okay? I don't drink coffee. I know it's surprising. You don't want to see me on coffee. It's more than this. So, great. So, multimodal representation. We're like, oh my gosh, I spent all this time. Finally, we're doing multimodal. So, multimodal representations, we'll look at joint representation and coordinated representations. My goal today is not to be exhaustive. I don't have the time to talk about every possible joint and coordinated representation, but we'll look at a subset of them to give you some examples. At any point in time, as usual, you're welcome to ask a question. So joint representation is probably one of the original representation. Some of the first paper on multimodal deep learning, and by the way, everybody who named their paper multimodal deep learning, and then everybody else is a subset of that paper. But yeah, this is the multimodal Boltzmann machine. What I like of Boltzmann machines, they have a lot of advantages. In fact, they are closer to graphical models than maybe some of the neurons, the feed-forward networks. They're great because they're usually trained in a joint manner, although you can do them incrementally. But they're also good, they're generative models, so you can go both ways. That allows you, from a joint representation, to generate image, and from the joint representation to generate text. So in a deep Boltzmann machine, I'm not going to go through the math for that. It's really interesting how to train it. They are quite a bit of pain to train. That's maybe a part of the reason they're not as popular these days. But one of the advantages, if you train one, which is really interesting, is the way to train it, one way at least to train it, is I give you a data set with paired data. Data set of paired data. What it means is a data set where I have images and description for that image, okay? And then I can use these images and text and train the model in such a way so that it can generate both image and text together. And now what's interesting is to look at the joint representation after that you learned this. You can learn this in an unsupervised manner, which I just mentioned, or you can learn it also in a supervised manner if you do a look at it as a retrieval task as well. You can do that. So that's these two different ways. But once you learn that joint representation, if I take any image, I can learn a joint representation, and not only can I learn a joint representation from that image, but I can go the other way around and learn and get a description of that. And vice versa, which is really cool, which some work these days are doing, from text, try to generate the image as well. It's not as well, it doesn't go as well the other way, but it does work a little bit. There was some work, early one, for retrieval, but I want to emphasize the autoencoder. You're like, oh, why did he talk about an autoencoder? You probably thought there was a multimodal version. Oh yeah.
Can you go into a little bit detail about how you train the multimodal RBM in a supervised way? Because I thought the way you train is quite contrasted with divergence, right?
Yeah, sorry, I misspoke when I said you train in a supervised way. So what I meant is you can, once you learn you can use that representation in another task. Sorry, I misspoke into that. So you learn in unsupervised or with contrasted divergence, But once you've learned it, then you can use that representation in a supervised task. And that's what they did in the paper, is that they use it for that representation. Is that representation better than, and one of the really cool aspects, I think, in this paper is that they had, I think, a visual recognition task. So, visual recognition task. Given an image, try to type the task. And you could imagine just learning a CNN for the image and use this for seeing how well you can do the task of object recognition or something. But now what they had is, instead of using this representation, like forget everything else, instead of using this representation, I'm going to use a joint representation for the same visual task. It's kind of a co-learning. I have a visual task, but instead of just using vision, I'm also going to use language to help you learn a better representation. And somehow, that representation that you learn with language ended up being better at the task of visual representation. I thought that was a nice result of that paper. The second type of approach that I want to discuss is multimodal autoencoder. And that's really interesting because you will have your audio representation and video representation, or it could be language and video, and then you will force the network to learn a joint representation, and then for that joint representation will need to have enough information in it to both encode audio and encode video. So you can see a little bit of the challenge that I talked about earlier. That joint representation not only needs to model what's joint or common to both audio and video, but it also needs to encode everything to recreate audio and everything to recreate video. So a lot of information needs to be encoded here to be able to do this task. Now, what's nice if you train this, what is really nice, is you can do some kind of ablation. Where is it? So you can remove audio. It's really nice. And then you can learn from video the share and generate both audio and video out of it. Okay? So you kind of have the same advantage as you had with the RBM, which being a generative model allow you to go both ways. But here you have it with a feed-forward network, and you can use one modality to generate both. That's one of the advantages, and you can remove the video the same way you can generate the audio. Another way that is more popular these days is multimodal autoencoder, which is the idea of encoding to intermediate representation, so then you decode. Usually you have the arrow the other way. I just realized that. Sorry, this is the right way. You do image and you want to get a caption. Okay? So this is if you were to do it in a multi-layer perceptron. Most of the time this would be more of a CNN and this would be more of an LSTM, but this is the general idea of an autoencoder, encoder-decoder approach. And finally, the most simplest one is a feed-forward joint representation. Feed-forward joint representation will have, in this case, we'll learn it through a supervised way. So let's say you are looking at text and images and trying to predict another task, like sentiment in this case. So I look at an image and a caption, and I want to estimate the sentiment out of this image. So this is great. This representation will bring the two together. There was a wonderful comment earlier that, if you don't mind, I share this intuition. I really like that intuition. So if I learn this representation, this is a joint representation for the sentiment task, I could go ahead and use that same representation for a new task, maybe emotion recognition. And that would be, I would call it joint representation. Someone was mentioning during the break that if I don't use this, I could also use these too. and these will be coordinated. And I thought that was a good intuition, and maybe a little bit confusing for some of you guys, but if you use these and not use these will be coordinated representation. Anyway, I thought it was a good intuition, but don't worry about this if you not get the intuition. But the general idea is that joint representation that you learn. But this joint representation is a concatenation of all the modality. It forces all of the modality, all the different type of interaction into that one vector. But if you think of it, how can we explicitly model unimodal, bimodal, and trimodal interaction? This is one thing that we have been studying in my group. This is one result from our group. How can you, in the case of sentiment, we love sentiment in NLP, sentiment analysis, multimodal sentiment analysis, how can I, from YouTube data, estimate text, image, and video, how can I estimate the sentiment? The simplest way is the joint representation, which we just described earlier. But if you think about it, how are text, video, and audio interacting together? And let me show you some example of interaction. There's unimodal interaction. Unimodal interaction means if I have someone say, this movie is sick, is it good or bad? At least in the US, it could be good or bad. At least that's what I realized when I moved to the US. Sick can be a good thing. I didn't think sick was a good thing, but sick is a good thing. This movie is fair. A fair will definitely be neutral or positive. If you see someone smiling, it has to be probably a little bit at least positive. But if you hear someone talking loudly could be loudly positive or very negative, but it doesn't tell you if it is in itself positive or negative. So unimodal interactions sometimes are clearly predictive, or sometimes you still have ambiguity. But let's look at bimodal interaction. If I say, this movie is sick, and you see a smile, this movie is sick with a smile, then it resolves the ambiguity. Now you start seeing bimodal interaction. Bimodal interaction because you have the smile and this movie is sick, or this movie is sick and a frown, then you will see more of a negative. And this movie is sick with a loud voice. What would be the sentiment? It's still ambiguous. Because, at least in the US, it could be really bad or really good. Okay, you're still ambiguous. Then you have trimodal interaction, where you have this movie is sick with the loud voice and the smile. Then it's clearly more positive. But then you have this really interesting effect. Even if I smile as much as I want and loud as much as you want, if I say something like this movie is fair, this is a strong lexical cue or a strong verbal cue, and that one will often override the other nonverbal. So this is an example of a trimodal interaction, meaning the three modalities together are not just adding each other. It's not just a summation of one plus another. There's nonlinearity, there's a complex interaction between that. So we want a representation that brings all of it together, unimodal, bimodal, and trimodal. And so for this, you want to go further than just a simple joint representation. You'd like to look at it in a more tensor fusion version of that. Tensor fusion is a really fancy term, and I must say, if I had to think of it again, I would not use the word fusion here because it goes against what was said earlier about fusion. But anyway, this is a representation that look at the product between your text representation and your image representation, and does this really simple but really nice trick of adding this one and below each of them. And what do you get when you do this? You get a matrix which has both the unimodal interaction and the bimodal interaction in it. By adding this one in your representation, you get both of them in your intermediate representation. And that brings the bimodal. And now you're like, hey, trimodal, watch out. Are you ready? So you can do the 3D version of that. Sorry if it seems that the color didn't go well. So the trimodal interaction of that. So this is here the trimodal components. Each of them, each of these units, if you look at it at the neuron, is a trimodal, the output of a trimodal interaction. That's what it is. Each of them, this one is the trimodal interaction of this dimension plus this dimension plus this dimension. And that's what the cube is. But since some cubes are unimodal in itself, you want to keep the unimodal representation and you want the bimodal, all of them together. So it's a simple extension, but very powerful. This will be presented in EMNLP. But this improves for sentiment analysis, has a significant improvement over state-of-the-art for sentiment. A lot of these state-of-the-art were either unimodal or multimodal, and the improvement over state-of-the-art is great, but more importantly, it also, and sorry if you don't see, but if you have language only, visual only, acoustic only, you have the bimodal, trimodal, and non-trimodal, but this is when you took all of them together. This is an important test because you want to be sure, is it really by putting all the unimodal, bimodal, and trimodal together that you get improvement? And yes, it is in this scale. This is true for sentiment. It may not be true for all multimodal cases, but if you have some task, multimodal task, where you know that there's more than just unimodal or bimodal interaction, and you need a representation to help for that, this is one example of this representation. Any questions? Yeah?
If I ask, what's the, it seems like you have a 3D tensor, there's a lot more parameters than like a regular
Yes.
design. So what's the computation cost in terms of, compared to like, just, yeah.
The number of parameters increase, but only for the last layer. So the rest of the network is mostly the same. It's just the tensor. The optimization, I don't know the exact time, but the training time was slightly more, but not significantly more, because most of the rest is all the same. It's really just this part of it. I have to find the exact numbers, but it's an improvement. But there is no requirements to change on the optimization, tweaking of things. This was mostly the same. But you definitely have an increase in number of parameters. This data set for Mosey was big, but not too big, 2,000 examples, and you still see an improvement in that, yeah.
May I ask a follow-up question?
Okay, yes, and then, yeah.
So, like, your tensor, it looks like you're assuming that it looks like there are a lot more parameters that try to model this, actually between like 3 different like data sources.
Yeah.
And like less parameter for like interaction between 2 of them, and then even less parameter for just like one source. Like, is this like fair assumption to make in this case, or?
You probably, one thing that will come to that is you probably want to put an attention or something on top of that or something to reduce the dimensionality. That's something where you or someone who should explore on top. But unimodal, trimodal, and if you think about it, you want to make it as, at least for smaller data sets, if you have an infinite amount of data, you don't have to think, you just run the usual machine learning. But if you have a relatively smaller data set, you need to have a model where if there is an evidence, meaning if there is something important in your data, it needs to be able to shine. And that at least my intuition here is, although we are increasing the dimensions, we're making it easier for the model to identify the important evidences in your data. I think that's the trade-off you have to see here. And in this case, that trade-off seems to be paying off, for at least for sentiment. But yeah, what you see here is the evidences, although you have less number of parameters, if there is something really correlated or really important in the unimodal, the model does find it out. And one reason for that is that if you don't use the unimodal, it does have lower performance than using the with and without the unimodal. You see performance. So unimodal, although it has less parameters, it does have an impact on the prediction. So yes.
I guess my question is like, say if you assume that like if you increase the parameter for unimodal and the bimodal, would that actually like boost the performance?
It would be interesting to try. That would be interesting to try. Although, what was the interest? What was the first question was if you use unimodal or not? Does it have a difference? And the answer is yes.
Yeah.
But now maybe you can do better.
Yeah.
And I hope you guys can find better representation than this. But already this does improve just on the joint representation. There was 1 and 2. Yeah.
You kind of touched on it already, but to follow up to his question,
Yeah.
how important is regularization in that expanded dimension set? Did you investigate, because you have many more dimensions, you exploded them, so does regularization help or does it not matter?
I believe this was done with no special dropout or any specific regularization. Since then, we've been playing with that, and I believe, there's a lot of interesting things to do to try to reduce that and still come almost the same number of dimensions to the other. This one was with no regularization, specific regularization in that, yeah.
So you already answered my question. What was the size of the data set? You said it's like 2,000.
2000, I forgot the exact number, 2,600. It's called MOSI if you want to do multimodal sentiment. That's a great data set. MOSI 2.0 is going to come out this fall, and it's going to be larger, stronger, better version of that as well. I want to go, oh yeah.
So you talk about the different modalities can be complementary or can be separated from each other. Could it be that they are controversial?
Controversial. What do you mean by that?
Like, let's say gray, but with the green face.
Oh, yeah. Okay. Great. Great. That's really interesting. Yeah. So intuitively, when you think of a simple multimodal, is kind of an additive model. Will be the simple model, which is different from what you mentioned. Is additive. Like if I say something that's more positive sentiment and my expression are positive, then I'm just adding. I keep adding them. That would be the simple multimodal fusion. But in certain cases, the sarcasm or something like this would be an example. And I believe a version of what I described will be able to handle it better than just forcing them to just be additive, is because if you allow to have unique unimodal events being able to be concatenated together, which gives something different than the other. So smile with a certain language could most of the time be positive, but smile with another type of linguistic or phrases will in fact be sarcastic and go the opposite way. And that, to be able to handle that, you need to give all these different options to your model. And so this is the exhaustive way of doing it. And I think you could think of maybe interesting way of contracting this. But I think the exhaustive way is a good way to start, because that allows the model to have events that are specific to each phrase and each nonverbal behavior. In the extreme case, you could have, in one dimension, every possible sentence you can say. I know, that's going to be long dimension. And every possible nonverbal behaviors you can say. And then you do the cross product of that. That would be a huge thing. You have to think of ways of summarizing that. But if you accept that it's feasible, then that kind of model that's exhaustive allows you to handle these sarcasm effect on that. So what it doesn't handle is if the same exact event can be interpreted more than one way, I think you will need something else to be able to, because of culture, let's say for example, the same thing will be perceived differently from different culture. I think it would be a different thing you will need to add on top of it as well to handle those different perception of the same event. which is maybe a different thing to discuss. Yeah. Great. Yeah.
It's a good question. So instead of, I wonder if you guys have compared, like, instead of explicitly parameterize with the first order, second order, third order interaction with the tensor like network.
Yeah.
Can you, if you guys, I wonder if you guys tried like just use the concatenated representation, but with a few more layers.
Yeah. This is the early fusion. Sorry, I didn't mention, and you probably can't read on that. And we tried. We really thought that early fusion will eventually cap. So we tried very different version of early fusion, large, narrow, deep, and all this. We did not, in our experiment, manage to find an early fusion, which is more of a joint representation that matches this. But that doesn't mean it does not exist. But we did not find that one. So, but we did try, I think, in the paper at least 5 or 6 version of that, and we could not find that one. Yeah, good. Coordinated multimodal representations. I want to give you one example for that because that's, and this is not our work, but this is really great work. This is about using a canonical correlation analysis to learn representation. So this is coordinated is the idea that you learn one representation for image, one representation for text, and you find some way of coordinating it. And that could be as simple as using a cosine distance. Although, I would say if you use cosine distance, these are going to start looking a lot the same. So I would say it's somewhere between coordinated and joint. But there's other ways, and by the way, if you do this way of just using cosine, when you do that, yes, they are kind of coordinated, but they are coordinated so strongly that if you use cosine distance, that they're mostly making them equal almost. At least their direction, not their length, but their direction would be. And this is when you get these beautiful results. Is in fact was the work on this was, although I introduced it as a joint representation, but really what they did there is coordinated in such a strong way with the cosine similarity that they're almost equal. So it's somewhere in between joint and coordinated. And that's where you get these beautiful examples of a blue car that become red, or flying that becomes sailing. So that was the example from that. But the coordinated that I want to give you an example is the canonical correlation analysis. So just so people who may or may not have done CCA before, it's a crash course on CCA mixed with multimodal. But canonical says reduce the simplest or clearest schema possible. That's what canonical means. The intuition that I gave you earlier, if I learn 2 representation, the first dimension may not match the first dimension of the language. That's the issue. Now I'm going to learn a representation in such a way that the first dimension of that representation is most correlated together. So I have my text. Oh, by the way, correlation mostly mean multiplication. Just to like so. So what does it mean? It means that I want these 2 to be as correlated as possible. I want them to be as correlated. So U and V are my first. So I have my text X, and I project U in such a way that I get HX. Okay? So the equation, if you had to do, is HX equal U times X. Okay? So I'm learning U. I want to learn U. What is this matrix U that will give me that new projection HX? And so I want to do that. I want to learn it in such a way that these are as correlated as possible. The correlation is really the same. So HX, I just rewrite HX here. That's a simple rewriting of the of multiplying. And now this is the same equation here. This is the intuition I gave you earlier. The correlation doesn't force it to be equal. It just means that I'm learning U, the vector U, that is the most correlated with the vector v. This is the argmax I want to do. I want to find a vector where x and v are the most correlated together. Okay? And that's something, this is the first step I will do. And then I will repeat this step over and over. So I learn how my data is the most correlated. And that's going to give you my first dimension. But then I need to have the second, the third, and the fourth. And that's where the canonical will come in, is I will not only do, we want to learn the multiple projection. You don't want to learn just one U, but you want multiple U. And the idea here is that you want them to be orthogonal to each other. Okay? And so to do that, there is a trick, which is the idea of the trace. You want the trace to this. Mostly what you want is zeroing out. You want, oh, here it is. I was searching the equation. So the idea is that if I have any of my projection, the data, if you take my data and project it on the first U, and take the same data and project it on the second U, they should be, if I multiply the two together, it should be equal to 0. Okay? So if I take any of them, J, and take any of the other dimension and multiply it by it, then it should be equal to 0. Okay? So it's just a simple way to be sure that they are orthogonal, all of them. So that's the second part of canonical correlation analysis. The third part is just a simple normalization. It's just a simple normalization. So at the end of the day, this is what you have here. And this equation is not that complex. This is my data, okay? This is mostly just x times y. This is covariance matrix. And then I project with the first projection for the modality 1, second projection for modality 2, and then I want to maximize the trace of it. By doing the trace, that's how I get the orthogonality from the trace. And then I just add this subject to keep the normal normalization on this. If you see this, maximize something subject to something else. What should you think of? How do you optimize that? He's French. Oh, he or she? He is French. Lagrange multipliers, okay? Okay, every time you see, or not every time, but most of the time if you see, maximize something subject to constraint, things Lagrange multipliers. It's a, do I have this slide? No, I don't have the slide here. But to optimize that, you can replace that and get one loss function that is using Lagrange multipliers. It can be done relatively simply. What is interesting is to start looking at this matrix. Really, this matrix has three things in it. Okay? It has X with itself, X and Y interaction, and Y and Y. And what do you end up with UV is you end up learning these parameters. So this is, in fact, the first canonical correlation. Lambda 1 is how correlated the X and the Y are for the first dimension, how correlated they are for the second dimension, and how correlated they are for the third dimension. This is what you end up encoding with the canonical correlation analysis. So to summarize, deep canonical correlation, or not the deep yet, is you learn linear projections that are the most correlated, that are orthogonal with each other, and has the unit variance of 1, or variance of 1 total. So as you can expect, and this is the beauty. I like this one. First the name. You have to give them the name. Deep canonically correlated autoencoder. I mean, this is a beautiful name. But what is interesting here is that I have an autoencoder for text. I have an autoencoder for images, but these will have some correlation together, some coordination. And this is, from my perspective, a great model. It is let's be correct. This is really challenging to optimize. And I think if you had to do work, it's to improve optimization of these. But conceptually, I like that kind of representation. Because you have a representation of you that contains all the necessary information to regenerate the text. So you know you've not lost anything because you're able to regenerate the text. So this is good in that sense. And you not only learn two representation, but you also learn how to coordinate them. So this one, this value, has a meaning that is related to this value. In fact, the length of hx would be the same length. No, does it need to be the same length? Yeah, it would be the same length as hy. So this is going to be the same length, but the meaning of this will have a meaning with this one. They're the most correlated. So I think this is a nice example of a deep canonical correlation analysis of a coordinated representation. Any question on representation and deep CCA and its extension? Okay, yeah?
For the last one, do we need analytics or
Yeah, you will need a pair of data set. Yeah, you can take advantage of unpaired data because you kind of have a hybrid loss function, which is part of it autoencoder, part of it the CCA. So you could imagine a learning strategy that takes advantage of the unpaired data. So you could work with hybrid data, which means paired and unpaired data as well. But you need some paired data for this loss function, yeah. Okay, yeah?
So also the first dimension of the x prime and the y prime, they're not related to each other anymore. True? When we do the...
They're not, these are not related to each other?
Are they, or that's the question.
Okay, so often when you train this kind of model, and there's a little bit of link with the previous question, is you're going to use data that is paired. By saying paired, it means that it's like image with its caption. So you're training, you have one data instance which is an image and its caption, and then another image and its caption. And so when you're training it, X and Y are related in the sense that they're paired. They're data that you know should be projected to the same similar space. So X prime and Y prime are related in that sense. But mathematically, if it was the question, you have in fact three loss functions here. You have the loss function of X prime, you have the loss function of Y prime, and you have the loss function of the correlation. And you're usually optimizing all three losses together.
So my question is that the first dimension of X prime and Y prime, what happens for them? Are they also kind of correlated with each other? Because it passes through the loss function in the middle. I don't know what happens after them. So I know that X and Y, the first dimensions are completely unrelated. What about the...
No, this will not be. So this first dimension will not be related to that first dimension because your goal is to, in fact, have these as close to these. So maybe a way these will be used, let's say, is you start not just from the one-hot representation for words. You could either start from one-hot representation for words or from word-to-vec. So if you start with one-hot or word-to-vec, this is also going to be one-hot or word-to-vec. And if you started with raw data pixel or with CNN, this is also going to be, so these are not going to be correlated. That was the question?
Yeah, so I'm wondering if these three objective functions kind of start conflict with each other, because hx and hy, it tries to make the dimensions correlated with each other, and then again when it goes to x prime and y prime, it just tries to be as it used to be, so uncorrelated. So one objective function tries to make it correlated, the other tries to make it more neutral, so I don't know if...
Yeah, I think this is why I mean, this is an issue with the optimization. They're definitely pushing different way. Part of it with the correlation, but part of it is they have different goals, really. One is to learn correlated, and then the other one is to regenerate the original data. That's why I think you're going to start seeing also hybrid representation eventually. One simple thing is you take this and you slice part of it, and maybe only part of it is correlated and part of it helps for the regeneration. There's some interesting residual approaches you could imagine. Let your imagination goes out. I probably gave you ideas for 2 or 3 papers right now. So yeah, but I agree that they're pushing different way. But fundamentally, I want to have a representation that does both, that is able to recreate the data, that has enough information to recreate the data. So fundamentally, I like this model. The details of the model, I think, is to be improved. But the fundamental concept of having enough information to recreate yourself, I think, and at the same time identify moments where you have correlation, I think is a good concept. And that's probably the take home. But your point is really good in this case, yeah. Okay, great. So the really quick, in fact, I'm probably going to skip most of it because of time. This is like 5 minutes on recurrent neural network. The reason for that is I'm using that notation later on for the next part of the talk. So recurrent neural network. So this is, by the way, what is Z again? Yeah, good. And then you have your loss function, and then you have Y, and then you have one layer neural network. And recurrent neural network, what they do is that they say, hey, as you are estimating your weight, your new age, you're gonna do it, your latent state, age, you're gonna do it, yes, based on your observation, but also based on the previous state. And that's easier to see when you unroll that. And so you've seen these recurrent neural network very often. What you may not realize is optimizing it is very easy in principle. At least computing a gradient is easy because before I go into the gradient, the one trick is that the weights are going to be tied between each time instance. So it's one set of weights or parameters for the whole neural network. So this is the same set of weights for time t as t plus 1, t plus 2. And now when you do the backpropagation through time, let me skip this one. When you do the backpropagation through time, it's the exact same thing. It's the chain rule, the exact same thing we did backpropagation. You remember, we start from it, gradient is 1, and then you compute the local gradient, that gives you the new gradient, local gradient times the previous gradient. You do the exact same thing, but you're going to do this also through time. So you compute the first gradient, and then you have the second gradient, which is the local gradient here, and then you just do the same equation. My gradient is the backpropagation gradient times the local gradient, and that's what you do over and over. You do it as you go down the aisle, but the main thing is when you start doing over time. Where it is? No, whoops. Anyway, when you start doing it over time, this H, the main difference between a neural network and a recurrent neural network is when you start looking at this variable H, this one will be dependent not only on the X, but also on the previous T. But because it's a chain rule, and as long as you don't have loops, backpropagation through time works really well. As you know also, recurrent neural network has the problem of vanishing gradient, and for that reason, they were extended into gated approaches. Gated approaches, and so I told you earlier there are different activation functions. Why do I use a tan H here? Because if my input here, H, was between minus infinity and plus infinity, or between -1 and 1, you often use a tan H there because you want to keep that same general range of values. And what I will do is I will start adding gates to it. First, it is a gate. This is the most important one, and this is why GRU are able to work with really few, less number of gates. This is the main one. What is it? It's doing a shortcut. it really do a shortcut. This one says, hey, I'm going to go and look at the cell, the memory cell from the previous unit, the previous LSTM, and shortcut it and allow you to go and ignore completely what was before and go directly. And this will be able to handle a lot of the vanishing gradient. Then after that, it's a bunch of little gates on top. So what you do here, this gate, this is the first gate. This is a sigmoid. Again, the intuition behind a sigmoid function is that it's 0 or 1. It decides how much do I trust the input, the latest input. How much do I trust it? Then you have the output gate, which is probably the least important of all of them. And finally, you have the forget gate that tells you mostly how much to shortcut, how much to just remember. So you could imagine I close the input gate and I let this one flow all the time. I mostly go constant. There's no vanishing gradient, I always constant. And then I slowly add, if I let the input gate, I slowly add evidences as you go along. So this is a crash course on LSTM. A small note, LSTM as we know it with the forget gate was not the original LSTM, but we still call it the LSTM. Forget gate was added a little bit later. So, and mathematically. LSTM are great. They can be used for multimodal data. I will show you some extension of LSTM that are really designed for multimodal data, but you can use them for multimodal data. You can simply increase your number and do early fusion. And as you know, you can do bidirectional LSTM. This is just the same thing. Often you just because LSTM are feed-forward networks, you will simply have a second one and then concatenate it together to do your Z. And you can make a deep version if you do that. Okay, so crash course on LSTM and recurrent neural network. The most interesting is translation and alignment. Translation is this idea of process of changing data from one modality to another. And with open-ended, and the same challenge we have in machine translation exists also in multimodal translation. And as I mentioned, there's two types, example-based and model-driven. Model-driven is probably the one you're the most aware of. If you see paper on image captioning these days, they're often model-based. How many of you publishers at ACM Multimedia? Okay, so if you go to a multimedia retrieval conference, a lot of this is in fact example-based. I have a lot of data, and a lot of this is paired already. So I have a lot of images with tags with it, and I want to do retrieval. So that's an example-based. So there's a lot of work on cross-media retrieval. Cross-media retrieval is, I have an image and I'd like to get a description, or the most probably the closest to what people would think is I have some text describing and I want the closest image to that. There is a way to do this, which is I have a data set with description and images, and what I do is I have a new description and I do nearest neighbor. I go for every description, try every description, and then find the closest one and return the image. Now this is the simplest version of that, the nearest neighbor, and then you can add a lot of flavors to that. This is the idea of retrieval, looking at it from retrieval. The magic in retrieval is often not this first step of retrieving. A lot of people in retrieval will put most of their energy in the second step, which is re-ranking. So once I found that these are the top matches, I will go ahead and re-rank them to find, and I will have another objective function for that. So this is one way of doing this. Whoops. The other approach is model-based. Model-based problem is more a parametric approach. So for example, you have an image, you encode it to CNN and decode it with RNN. That means that this is your parameters, this is your model, and then you can use that with a new data set, and then you can use new images and use the same parameters, and you can see the difference between the non-parametrics and the parametric approach there. Extension, by the way, this is one of the challenges with image captioning is evaluation. If you're given a caption, how good that caption is, the same thing as in machine translation. So the field of multimodal have been moving more towards other tasks, like visual question answer. The advantage of there is evaluation. I ask you a question and supposedly there's only one answer to it. So because there's only one answer, or a really few set of answers, then I can evaluate if you really understood or really predicted correctly or performed the translation correctly. So visual question answer is kind of a double translation problem. You go from a question, look at the image, and then get a text answer. So text, image, text. This is an example of that. And now these days, there's also another field that's interesting is referring expression, which is another interesting aspect, which is I have an image and I'm referring maybe to only one object in that image. So from an evaluation perspective, this is great. There's maybe only one image, one object, sorry, that's relevant to my referring expression. So the camera on the right, which is kind of interesting because for all of you guys it's the wrong one. But the camera on the right, there's two cameras, but I want to point one of them. If you do it for nonverbal, it will be easy. But from a language perspective, you will do it more as the camera, the tallest camera. So it's the tallest camera, and you could imagine other referring expression. So there's not only, it's not a one-to-one mapping, it's a many-to-one mapping. There's more than one referring expression that matches one object. But the basic idea here is evaluation. And I will not spend time on evaluation because there's probably experts here who will know even more about how to evaluate machine translation. But what's really sad and happy and sad is that all the challenges that you have in machine translation, they are there in image captioning, and people are trying to find better, standards for, and there's what the Microsoft folks, they created another one also, and yeah, they're all French words, originally bleu, rouge, and I think there's more than that. But the challenge I will say for translation is evaluation. That's, I think, one of the main challenges for translation. I want to spend most of my time on alignment because that's, I think, really fundamentally a multimodal problem. So I want to give you example of explicit alignment and implicit alignment. I want to give you example for both. So how many of you have worked with dynamic time warping? Okay, a few. Okay, so explicit alignment is, as I mentioned earlier, my task is about alignment. My goal, ultimate goal is aligning to. So I have, for example, maybe a video, and I have maybe motion capture. I may have even, in fact, voice that I want to align to the video. Or I have, in fact, example of one person kicking and a separate second person kicking, and I want to align these two videos of two people kicking and align them the best I can. So this is often alignment or explicit alignment is often done on sequences. So the basic approach for this that has been is dynamic time warping. And so let me go through this slide. It looks overwhelming. It's not overwhelming. It's easy. So I have a first signal, me kicking. And then I have another signal of another person kicking. And let's say it's a motion capture. So X is all of the points of the motion capture. That's one vector, maybe 46 dimension over time. And then you have the other person. And you want to do the mapping between them. And I end up kicking faster, and the second person ended up maybe kicking slower. Okay? So you want to be able to align it. And the way to align it is to say, for each of these frames, which of them is the better match in the second. And so this is what you see here visually, is the best match for this is in fact these 3 frames. In fact, because I went so fast, I had the frame that is seen in the other sequence in a slower pace. And the best thing I can do is match these together. And so this equation is just doing the same thing. Your loss function is going to be part of these index vectors. The index vector says for x, for each of these x, what is the y that is the best match to it. So if each of these points have index 1, 2, 3, 4, 5, 6, 7, then that will give me index. So by indexing these, I'm trying to find the loss function. If you were to put it in a complete form, you find the px and py. I think I have it somewhere. I will have it in the next slide. That you want these index that optimize this loss function, that are the closest to each other. And in fact, this, from a dynamic time warping perspective, you want to see it almost as a path. This is kind of a path to go from there to there, to the 2 endpoints. And in fact, there are many different ways of going from one to another. And what dynamic time warping is finding kind of the easiest path. Or the low cost. And so you want the key of dynamic time warping is to define a cost function, which is mostly a similarity. How close my current position is from the positions, all of the other positions there. So the simple exhaustive way is I look at this one and I look at all of the frames here and find the closest one. So that would be the exhaustive way. But I don't want to just find the closest one. I want it to be smooth over time. That's the second important thing. So if this one looks a lot like this last frame, I don't want my first frame to look a lot like the last frame of the other. So you want time consistency. So that's why it's more than just finding the nearest neighbor. So dynamic time warping what's nice with it is that there's an alternate representation to it. One is through the indices that I told you about. So you have different index. But you can also do it and repeat each of these cases that have more than one and repeat them, and that doesn't change the objective function. So you can change this objective function into a matrix representation, which is really nice, because now I have a matrix representation. This is this representation, and now for every time there's a one-to-many link, I will duplicate it, and then I get a matrix, which is just a matrix that links which one links, and this one will be monolithic. This one will have a clear path into it. That's my goal eventually. So this is the formulation, and and this can be different kind. Or usually you have different kind of norm for that. But the reason I put it in a matrix format is that now I can start extending this work. Because what did I do up to now? I only did it between 2 instances. Okay? I have this. And I have this. But what if I had a third one? Okay? So it's not just trying to align 2, but I would like to align 3 of them together. The complexity with the previous approach becomes really challenging. And the 2 other thing is, up to now I only did unimodal, and we are the multimodal, so we want to be multimodal. So what happened when we want to do multimodal? Oh, CCA is back. CCA is back. Why CCA is back? If I have if X and Y are in the same exact representation, then it's easy finding the score function or the cost function. It's just like, how is this looking like this? But what if I have mocap and a 2D image of the person? These are very different. So you can use CCA also to learn representations, coordinated representation almost, where I will be able to do the dynamic time warping. So I will take the mocap, learn a representation for the mocap, and learn a representation for image where there is correlation, and then do the dynamic time warping on top of that. So I can use the CCA. This is the same equation earlier, but this is the representation. This is what I told you earlier, but there's another way of writing CCA in matrix format. That is a simple extension, and once you put it in a matrix format like this, then you can bring the two together, and that's how you get canonical time warping. Beautiful. I give all the credit to Fernando. So what do I have here? So UX, what does it do? It takes the mocap and creates a projection, and then V is creating my image and creating a projection that are correlated. And then the W are there to do the dynamic time warping, the alignment. So it does both together, and what's nice is it can be generalized to not only 2, but to as many as you want. So I am trying to align, so it can be not just 1. Here you had only U and V, but you can generalize this through this matrix. And so if you do that, you get these beautiful alignment between someone walking quickly versus someone walking slowly. You can align the frames. You can do it between modalities. I think that's it here. So this is 3 different data sets, completely different data sets. One is a mocap data set. One is probably the most famous Swedish action data set, blanking on its name, and someone doing it also similar one. So this is all aligning different modalities together, and you're like, oh, he didn't say deep yet. So yes, there is a deep version of that. Yes, there's a deep canonical time warping. Someone had to do it. I think it's Maya's group who's done it. But yeah, and the reason for that is I told you I am learning a new space, but right now it was a linear mapping. By doing the deep, I'm making it a non-linear mapping. So from my observation, non-linear, from the other observation, non-linear, and then you do the DTW between them. So it's beautiful. It's putting everything together. It's the same equation. So this is my observation. I learned this new space, but instead of being a linear, it's a non-linear. And then I learned this alignment between them. So this is examples of explicit alignment. My task is alignment. Now there's implicit alignment. Implicit alignment is, and I will use machine translation because, in fact, some of the earlier work on implicit alignment are from machine translation. Dog on the beach, le chien sur la plage. Given a sentence in one language, translate to another. You guys knew what machine translation was, but just in case. It's not multimodal, but it's a good start. So we'll go with this. So typical machine translation these days, neural machine translation, although there's a beautiful paper on neural machine translation and visualization. But let's say for now we believe in neural machine translation. So we learn, encode one sentence, learn that intermediate representation, and then can use it to decode in the other language. So this will be learn usually end to end. So we'll learn how to encode each word to eventually get, so this will be an LSTM or some recurrent neural network. This will be some kind of intermediate representation that will be used for the generation of the, in the other language. Now, what is the beauty here is to add the attention in a machine translation model. And so you've seen that for machine translation, so I'm just going to show. So what it is le chien sur la plage, when you're trying to translate that in English, the ordering of adjective and nouns in different language will be often swapped. So you want to be able to not only attend to the last encoding or not only attend to the exact same position, but you want to be allowed to change where you attend. So when I start decoding, at this point I decoded the dog. Now I will, before decoding the next word, I will look back. I will have an attention model that will decide which of words to look next and use that information to decode, and then you can repeat this over and over. What's the beauty of this is if you look at this attention, because, okay, people are often asking me the difference between attention and a gate. Although attention sometimes is used differently, conceptually, an attention is a scalar, is one number, okay? So, what it means is one scalar for how much to attend to the first word, another scalar to attend to the second word, another scalar to attend to the third word, fourth word, and sixth. Okay, so you have one scalar that tells you, okay, I have an encoding for le. I will trust this, or in fact, how much do I focus by one number, one scalar. And then it's a kind of a weighted summation. So I have the encoding of le, kind of word to vec of le, and I multiply by the attention for le, plus the encoding for chien. I multiply by the attention for chien, and I do it for each of them. This is how the typical attention works. Now, you could do a gating version of that. The gating version of that will say, for each, let's say the dimension is 300 here. Instead of having a scalar, I could also have another vector, a gate, the output of a gate, of length 300, that will tell me for each dimension of the encoding of words, le, which one should I trust, or which one should I focus on. But the advantage of the attention, which is a downside at the same time, is that you have only one scalar to do the whole attention for the word. So it's one scalar for each. But there is some extension that people are still using the word attention, but in fact what they're doing is a gate, is the same size. So just to be aware that people are using the word attention as an attention scalar or score, but some people are also using the word attention for a gate, which is, in my point of view, is different because it's not interpretable. But the nice thing when you do scalars is that you can look back and look at which words were used when you do the transcription, when you did the translation. And as expected, because of English and French, there is a nice zone économique européenne, European Economic Area. There is a nice swap into the attention. So, but now, looking back at multimodal, you can do the same thing. But I have an image of 300 by 300. How do I define attention on an image of 300 by 300? Or let's say even 32 by 32. How do I attend? How do I define? So earlier I had words. So I had a set of words. I had a sentence. I can either attend to the first word, second word, third word. But in an image, how do I do this? So the trick people did is when you do CNN, you do a CNN on an image, let's say, of 64 by 64. Your first kernel will be maybe of size 4 by 4, 3 by 3. So really local. The next layer will be concatenation, or bring together small pieces of the image into larger part of the image. And so the area used by the kernels at the second layer is go over a larger piece of the image. So the first layer is only over 4 by 4. The next layer will be over 16 by 16. The next layer will be 64 by 64. If you stop at the third layer, you have a kernel that is automatically over a larger portion. And if you look at a CNN, the last layer, there is a 16, if you look at AlexNet, which was one of the original CNN, the last layer was 16 by 16. Okay? An image of 64 by 64 ended up 16 by 16. So, as good computer scientists, they use that last layer of convolution as the different option. In other words, what they end up doing, which is really simple, and I believe there's a better solution, but given an image, what they end up doing is slicing it 16 by 16. So given an image, there is how many words you can focus on? 16 times 16, which equal, no, I don't know 16 times 16. Someone, yeah, come on, okay. No, but this is the number. So I'm about to do my generation, okay? I'm about to do my generation. Where should I look in the image? I have 16 times 16 words I can focus on. And then I will decide which of these words are the most useful for predicting the next, I call them words, but really is subpart of the image. Which one are the most useful? And then I will use that with the previous word to predict the next word, and then I go vice versa. Then I check where I should predict next. So at this point, I predicted the next word. But when I predict the next word, I also predict the attention. So this, what is the dimension of this? 16 times 16. Okay? So it's 16 times 16 scalars that tells me where to go look back in the image. This is 16 times 16 image. And then I will use that here to finally predict the next word and also the next attention that will tell me and do it over and over. So it becomes, so what did I do? I added two things. It's not only just generation, LSTM, previous word, I predict the next word, but I also predict the next attention, which will give me the next encoding of the image. So this is the attention model that you will use. The attention model use the encoding over, and here's the, now we should be able to read. A woman is throwing a frisbee in a park, dot. Okay, so it could be everybody. Woman, it turned out that both of them are women, is throwing, definitely more this person, frisbee, more here, in, that's really interesting. That's one of the challenges of these attention model, is they force, some words do not have a direct mapping on the image, but you do force it to be. And then park is everywhere but the two people. So park is everywhere. So the white tells you where you're focusing on the image. Attention can all be extended to videos. And that is something that is really interesting that was discussed earlier about granularity, segmentations. If you seeing me talking and you make a judgment how good of a speaker I am. Okay? Let's say you're making a judgment how good of a speaker I am. We're making this judgment based on a few evidences. Okay? I talked for 2 hours. It's not all 2 hours of me talking that makes you decide or judge how good of a speaker I am. It's a few cases, a few moments where maybe I look left and right. There's a few behaviors that really made your mind in your judgment. This is also true when you recognize an event, like a jump or someone cooking or something like this. It's not every frames in the image that is relevant. Only a subset of these frames may be relevant. So you can take the same idea of attention and apply it over a video or any kind of sequences. So you get an observation, and then what you will do is using a simple bidirectional RNN. It turned out that RNN are sufficient for that task. You can use more complex, but RNN are sufficient. You will learn the saliency score. How important is this observation? And then, here's the beauty, is you're going to learn a recurrent attention gate. And the attention gate has the same idea of the previous kind of GRU or LSTM, but the goal is slightly different. So what is this? If, for this frame, if it tells me don't attend to this frame, this is a bad frame, And bad frame could be for two reasons. One, there's nothing in the content of it. Or second, there's something about the noise. It's too noisy. Okay? So if it tells you that, what do you want? Then you want this to simply bypass. And what was the previous event state? You want it to simply bypass and go directly. But if the attention is high, then you want to be able to take into consideration that observation and integrate that into this. So the attention gate is simply deciding based, this recurrent attention gate based on the attention, either here or here, decide to either bypass or integrate the information. Really simple. But that very simple approach, in fact, does really well both for video representation, so video event recognition, so you want to recognize a birthday, or biking, or wedding. You want to be, and just using LSTM or tag, and by the way, the number of parameters for this is the same. They're the same, about the same number of parameters. So it's not that you have more parameters in here. And let me show the video on this. So the attention for biking is obvious. There's only one biking. So there's clearly one moment where you see the object. Baseball is more interesting. So at the beginning, it's not clear, but then you see the field of view. So then you definitely have more attention at this point. You see a large person, like the broadcast, and the field again. And by the way, this is at some point you're going to see again the field of it. And this can be done on text also. I think there was a paper last year that did something similar where you also, oh my gosh, you guys can't read anything, so you have to trust me. But one thing that, where is it? Don't find. But it predicts also words that are, like if you have good and not good, it will predict correctly to find both the not good and just not just good but not good. So you can do this on sentiment as well, improve performance by a large margin and that. So the last part of the tutorial, stretch, okay? Okay, good, you're good, okay. Multimodal fusion. Multimodal fusion, as we talk about, used to be only two ways: early fusion, which simply concatenate the modalities and then you have any classifier, or eventually has late fusion. So the advantage and disadvantage, I don't want to spend too much time on early versus late fusion, but the advantage of early fusion, if you have any interaction between your modalities, you want to do early fusion because you want to learn these interaction. But if the interaction between the modalities is only at the decision level, then late fusion is a better approach. The bottom line is, if you don't have a lot of data, I usually always tell students to start with late fusion. But if you have enough data, you want to learn the interaction with your data, with your modalities, then early fusion works better. But this is things I was telling my student 10 years ago. Now we don't do this. A hybrid is just a version of that puts them together. Someone did that at some point. But I want to give you three main approaches. Okay, there's all the deep learning. Okay, well, we're going to imagine for a second that is a little bit more than deep learning. So multi-kernel learning is the so support vector machine. For people who may or may not know as much details, in a very simplistic manner, support vector machine will take your data, project it in a hyperspace, in a really high dimensional space, define a hyperplane that best separates your data, and then you have also optimization through the hinge loss that also optimize the distance to the hyperplane. That's in a really simplistic manner SVM. The interesting part is, how do you learn that projection from that normal feature representation to this higher dimensional space? The reason you will do that, the real reason, is to learn a similarity between two samples. I give you an example, I give you another example, and I ask you, are they similar? If you look at this to have a similarity matrix, it makes sense to have a different similarity matrix for visual than from audio. So multi-kernel learning is extending the idea of support vector machine, where you're learning a different kind of space on how to compare audio segment to visual segment in different modalities. There has been also work on graphical models. I know 10 years ago everybody was doing conditional random field. So these extensions will use not only trying to predict one label, but trying to predict label that learn these latent variable. And latent variable, as I mentioned, the idea intuition is clustering. So it's learning how to cluster your observation for audio, learning how to cluster your observation for video, and then learning how to synchronize them together. That's an example of, but I would, probably by now you're like, okay, I want to get an example of a fusion. And I put it in a category fusion, but it could be representation, but we're not going to get back onto that. But I want to do classification, sequence classification. And if I want to do a multimodal, I have multiple modalities, I could simply learn and concatenate them. Okay, that's probably the idea. So let's say I do emotion recognition. So you hear my voice, you can hear the words, and you have the nonverbal at the same time. So that's three modalities, and I'm predicting the emotion. Okay, this is the idea for LSTM used for multimodal data. But this is really simplistic. I would like to have a multi-view LSTM. Multi-view LSTM. What is a multi-view LSTM? Okay, so multi-view LSTM has as input the audio input, visual input, and language input. The main difference with the unimodal LSTM used earlier is that I will also have three hidden states. One that is related to language, one related to vision, and one related to audio. So you have three hidden states. This is, you remember the tan H? The tan H is there and also keeping -1 to 1, okay? This is the first gate. So this is just integrating your observation. Then you have your input gate that comes in and decides. It's a sigmoid again because deciding what goes on and up. The most important is the multiple memory. That's the main difference between LSTM and multi-view LSTM, is you have memory for each of the modalities. And then you can decide what you remember from each of them, and the same way you have your output gate. So one version of that, which would be decoupled, would be equivalent to have three separate LSTM. But the beauty of it is how do you couple the different modality? And the main important thing is here. How do you couple the different? Because if this one was only related to this one, was only related to this one, and this one, that would be just a separate LSTM. And if this one is you get the idea. But here, we're going to change different topologies and try different topologies. And for this, we'll have two design hyperparameters. How much memory from the current view and how much memory from other views. So one topology is the view specific. I only trust my current view, which mostly means I only have three separate LSTM. Okay? The other extreme version is the coupled one. Is in fact, when it comes time to here compute the observation, I'm going to compute the hidden state only based on the other modality. What it means is the GT1 will be based, not based on HT-1, but based on the other modalities. This is coupling. And if you know HMM, there's coupled HMM that does also the same kind of coupling. But these are two extreme cases. Now what's more interesting is how you start fully connected or hybrid version of that. And I think this is where there's a lot more work to be done on how do you create these hybrid connections. And here I present for GT1, which is this one, but this is repeated for GT2 and GT3. I just didn't show them here. And so you have to decide, when I keep my memory for time t, for my language, how much should I integrate from vision and how much should I integrate from audio when I do this integration over time? And if you do this, you get improvement, these hybrid LSTM over a simple LSTM or fully connected version of that. So that's the take-home message from that. And this is really a first attempt at this, but I think this kind of hybrid, where part of the memory is used for commonality and part of it is view-specific. So you have view-specific memory and common memory all in the same LSTM. I think that's the beauty of it. So, oh yeah.
So the parameters here were learned, or was it like hyperparameter set?
These are hyperparameters. So this will be learned, and there is in the paper some analysis. They're quite smooth. They're not jiggery, but these are learned automatically. So let's say if you say what's not shown there, if you say view specific, let's say 50% and 50%. If you say 0.5 and 0.5, okay, what you end up earning is your memory. 50% of it will be from your view specific. So you have 300 dimension, let's say. 150 dimension will be view specific, and 150 will be view specific, and 150 will be specific to the other views. And then you can start creating some interesting overlap also between them, yeah. But these are learned hyperparameters. But I think there's interesting design on how to design this, yeah.
I'm wondering if, like this, I can't remember the name before, and that was the multiple dimensional.
Oh yeah, and that will be.
Having not a matrix or a tensor of parameters, and then there,
that would be wonderful, yeah. Great. So this is my last slide. I thank you all for the attention. This their take-home message. When you look at multimodal, think more than early-late fusion. Think about representation, alignment, fusion, translation. And I did not have as much time for co-learning, but I think this is one area there is the most interest, is how one modality can help another modality. So thank you very much for your attention. Thank you. I will stay here. If there is more questions, I can answer any questions, but otherwise enjoy your lunch. Thank you all.